every morning you have two choices. Every morning you have two choices. Continue to sleep with your dreams or wake up and chase them. So, hello, my shimmering stars. I, Shaurya, is going to start our one shot lecture on general organic chemistry. Students, as you all know, in our victory batch, we have already covered IUPAC and isomerism. Now, the third topic is going to be general organic chemistry, which is going to be very, very important for your competitive exams. Now, students, if I move forward in what topic we are going to start today is, first of all, we need to know why there is a need for general organic chemistry and how we are going to proceed in this further lecture. So students, first of all, the need for general organic chemistry arises due to organic reactions. If I talk about a simple organic reaction, I would say what comes in my mind. In my mind comes that reactants gives product. What happens in reactants? Old bond breaks and new bonds are made, that is the product formation. So if I talk generally, what do you mean by any reaction? I would say generally a chemical reaction involves a reactant in which bond breakage occurs, that means old bond breaks, and hence we get products in which new bonds are formed. But in actual, students, this is not the correct order of the organic reaction. How does an organic reaction occurs? First of all, we require a substrate. What happens? How does an organic reaction occurs? This was our basic, the definition, I would say, for organic reaction. Now, what actual is organic reaction? I would say we require substrate. What we require? Substrate. Now, there is an attacking reagent which attacks on the substrate in the presence of some medium that is known as solvent. So, what happens? On substrate, attacking reagent attacks in the presence of medium, which can either lead to the formation of transition state or to the formation of intermediate first, which can either lead to the formation of transition state or it would lead to the formation of intermediates, or you would say reaction intermediates. It's the same thing, right? Which further, students, which further gives us product. So this is the actual meaning of organic reaction, or how does an organic reaction occurs. Now, if I talk about substrate or attacking reagent, now which substrate I should use or what kind of attacking reagent is required for in particular organic reaction to occur, I would say this all depends upon electron density. If the electron density is high or the electron density is low, the attacking reagent will be with respect to the electron density it would attack. If I say the electron density of the substrate is high, then the attacking reagent which is attacking on the substrate will have electron density low. And if I say here the substrate which is present has electron density less, now the attacking reagent which is going to react with it will have electron density more. So it is vice versa for both of these cases, right? So this all depends upon what? Electron density. Now what we are going to see, first of all, we are going to study about substrate. That means in the substrate we are going to see the electronic displacement concept. What we are going to see? We are going to see under this, first of all, I'm writing electron density because it depends upon electron density. Second thing, we are going to cover here about electronic displacement. We are going to cover about electronic displacement. Then, as I told you that depending upon the substrate, there is a something, I would say, attacking reagent that is going to react with it. So if electron density, students, if I would say it is less, then electrophile will attack. If it is more, then nucleophile will attack. So in attacking reagent topic, we are going to study about electrophiles and nucleophiles. Here we will cover these kinds of topics, electrophiles as well as nucleophiles. Okay, now if I talk about the medium, here we are going to study about the solvent in which it is going to react, right? Here we are going to see about the solvent. Now the next step comes the transition state, or I would say intermediate. Now what is the transition state? Again, where old bonds are broken in and new bonds are made, right? And if I talk about intermediates, which is going to be the very most important topic in the GOC, that is intermediate. It can be carbocation, it can be carboanion, it can be carbon free radical. So here we are going to see the three categories, that is carbocation. The second one we are going to see is carbanion, and the last one we are going to see is carbon free radical. Clear? So this is going to be the the way in which we are going to study the GOC. First of all, we are going to study about electronic displacement, then we will move forward towards electrophiles, nucleophiles, and further towards the carbocation, carboanion, and carbon free radical. So one by one we are going to understand the general concept of any organic reaction, right? Now see, students, if I talk about the very first concept, that is electronic displacement. As the word itself says, electronic refers to the electron and displacement refers to the movement. So what is here seen? Electronic refers to what? It refers to electron, while displacement refers to what? Movement. So what we are going to see here, we are going to see the movement of electron. We are going to observe the use of arrows in the general reactions. You would have seen in many of the cases while solving the question papers or while attempting the questions, we generally observe that there is a use of arrow in resonance, you have seen, right? So I will tell you how to use arrow in which direction, or how we are going to see the movement of electron from one position to another position, how the electron movement is being shown with the help of certain diagrams. So one by one we are going to understand the very basic concepts of organic that we need to understand, and if we get this basic concept, then further organic chemistry is very, very easy for you people. Now students, as I said you, electronic displacement is the movement of electrons that we are going to see. Here we are going to check about electron density. Where is electron density more or where is electron density less, right? Now if I talk about the types of electronic displacement, that is of two types. Now this is of two types, students. One is permanent and another one is temporary. One is permanent and another one is temporary. Now, if I talk about the kind of permanent effects, now these are further classified into three subcategories. Now, what are these three subcategories? The number first that we are going to start today is all about inductive effect. Number first is inductive effect. Inductive effect. The second that we are going to study over here is going to be resonance or mesomeric effect, or mesomeric effect. And the third one, which we are going to observe over here only, that is going to be hyperconjugation. Hyperconjugation. Now, if I talk about the temporary effects, students, if I talk about the temporary ones are classified into electromeric effect. It contains electromeric effect. Okay, now as it is temporary, we are going to say here only at a certain limit of time we see the attacking reagent is attacking. So we will see what is the permanent effect that lasts for a long time, and temporary is the one which doesn't last for a long time. So these are the types of electronic displacement which are further classified into permanent and into temporary. Permanent are further classified into what? It is further classified into inductive effect, which is represented by capital I. If I talk about resonance or mesomeric effect, I would say it is represented by M or R. Okay, and if I talk about hyperconjugation, it is represented by H, or you directly write hyperconjugation, right? And the last one is electromeric effect, which is a temporary kind of effect. Now further moving to the next topic, I would say let us take some general knowledge that is going to help us in the organic chemistry today. Okay, so what is the general knowledge that we require here? What is the general knowledge required over here? Now here I will be talking you about electronegativity. What do you mean by electronegativity? First of all, I want you people to answer me. Electronegativity, as I've already explained you in some of the cases, that electronegativity is basically, the attraction of certain pair of electrons, the tendency to attract certain pair of electrons. That is electronegativity, right? So according to electronegativity, if I say there are two atoms that are bonded, A and B are the two atoms. Now, if I would say A and B are bonded with each other, if I would say A and B are bonded, then how many electrons are present between this bond? You will say, ma'am, 2 electrons, because one bond contains 2 electrons. So yes, one bond contains 2 electrons. That means here, which kind of bond do you observe? Here is sharing of electrons. Here is sharing of electrons, right? Now this sharing of electron occurs in which case? In covalent bond. So this is a kind of covalent bond, right, ma'am? Okay, now let me tell you one more thing, students. If I talk about electronegativity and if I say, if I have this AB molecule with me and B is the more electronegative atom, so what would you say? If I say in this AB, B is more electronegative than A. So what kind of thing that you observe over here? You will say that, ma'am, if B is more electronegative than A, then that means that B has more tendency to attract the electrons, the shared pair of electrons. Now there is a bond that contains 2 electrons. Now what will happen? There will be a shift of electrons towards B. It is sharing with A, no doubt it is sharing with A, but there is a kind of pull towards B. Why there is a pull towards B? Because B is more electronegative. Due to the electronegativity tendency, it will attract the electron towards itself. It will not break the bond and separate. No, it will just attract. It will just pull the electron towards it. So we can see a bit of shift of this electron towards B. First it was seen that electrons are present in such a situation, but now it is shifted towards this. Now when you are, when electrons are approaching towards you, you will attain which charge? You will attain negative charge. And when electrons are moving apart from you, which kind of charge do you develop? Positive charge. You know that, no? When there is a deficiency of electron, positive charge arises. But when you have electron, you have a particular kind of electron, then you gain which charge? Negative. So here B has a shift of electron towards itself, so it will acquire partial negative charge, while A will acquire partial positive charge. Now this is the basic thing that I want you people to understand, the charges. This is what? This is the polarization of sigma electron. Here what is happening? Here what is happening? Here is polarization. Here is polarization of sigma electrons. Why I said sigma electrons? Because it is a sigma bond. It is a single bond, right? Now electrons are polarized. That means poles are arising. Positive and negative poles are being arised. So here there is a shift of electron towards B, a little more than A, right? So here bond is not broken, but there is a shift. Here what was happening? Here was a sharing of electrons, and that was the covalent bond. Now let us take one more example. Let us take one more example to understand one more concept in depth. If I say carbon, 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 and here fluorine is attached. Now you all people should be aware of this thing that, here fluorine is attached, sorry. So fluorine is what? Fluorine is more electronegative atom than carbon. This is the basic thing that you need to keep in your mind if you have your inorganic concept a little bit weak. So I am directly telling you that fluorine is more electronegative than carbon. Okay, now if fluorine is more electronegative than carbon, then it is going to attract electron towards itself, right? Because it has tendency to attract, not to break the bond, just to attract, just to pull like this bee, right? So if it has that tendency, now here electrons will be shifted towards this, so it will acquire partial negative charge, while this carbon will acquire partial positive charge. So again, here in this bond, here over this bond, I would say what is happening, polarization of sigma electrons again here, right? Now what happens over here, students, what happens over here, there is a little bit pull of electron towards the F, right? Another thing that you need to keep in your mind while solving the question is, sometimes you don't know which is the more electronegative atom. Like if we generally talk in the case of carbon, you are given different cases of carbon, then in that case you need to find the hybridization of carbon. You know, the percentage S character is directly proportional to electronegativity. So whenever in the cases of carbon, when you are not given any electronegative atom and you are being confused when there is a double bond or a triple bond, how you can calculate which is more electronegative atom, which carbon is more electronegative. So in that case, what you need to keep in your mind, that percentage S character is directly proportional to negativity. So in this case, what happens, students, if you keep this point in your mind, first of all, what you'll do, you'll calculate the hybridization for each carbon atom. You know, when you'll calculate the hybridization for each carbon atom, you are going to get what? You are going to get sp hybridized, sp2 hybridized, sp3 hybridized carbon atom, right? You are going to get this hybridization. Now, which will have more electronegativity? The question arises, which has more S character. Now, how to check more S character? See, you know, there is 1S, 1P. That means if I divide by 100, that means 50-50% both the characters are present. If I talk about sp2, how many S? 1S. How many P? 2P. That means total is a sum of 3. If I divide it again by 100, it is 33.3%. That means individually S is 33.3%, 1P is 33.3%, another P is also 33.3%. If I talk about sp3, what do I observe over here? 1S and 3P are present. The sum is 4. Now again I divide by 100, 25% comes. That if I talk here, percentage S character in sp is about 50%. If I talk over sp2 here, I would say the percentage S character over here is 33.3%. While if I talk in the sp3 kind of situation, students, we see 25%. So where is S character more? In sp, then in sp2, then in sp3. Hence, as we know, S character is directly proportional to electronegativity. So the order for electronegativity is going to be this. So it's clear for you. Now you are able to identify when it is given like this or when it is not given like this. Okay, now one more case that you are going to observe in the coming questions is, for example, you are given such a situation. Now, if I say, kindly do the polarization of the sigma electrons, will you able to do the polarization of sigma electrons? So your answer would be no, ma'am. Why? Because there are same atoms present over here. Whenever you are having same atoms, so no polarization occurs in carbon-carbon bond, because all are same, all of the hybridization is same. So neither we can follow this concept of more electronegativity, nor we can follow this concept of S character when all the, you know, hybridization is equal. So here no polarization occurs. No polarization occurs over same carbon atom. Clear? So these are the basic things that you are going to observe in the coming part. Okay, now moving to the coming part, first of all, I want you all to understand an order for electronegativity also that you already know, but let me tell you again. Fluorine is the most electronegative atom, then comes oxygen, then comes nitrogen, then comes carbon, and then comes hydrogen. This you are going to observe generally. So if you don't remember electronegativity concept, no need to worry. Electronegativity is a tendency to attract shared pair of electrons, and the atoms whose electronegativity you require, I'm just writing those. Fluorine is more electronegativity negative, then oxygen, then nitrogen, then carbon, and then is the hydrogen. So this order, if you remember, the questions are going to be easy for you people. Other than this, students, if I talk about, you know, three cases. If I talk about three cases, the first case I would say is A negative. The first case I would say, again the order for electronegativity, or I would say, let us not say for electronegativity, let us say for electron density. Where is electron density more? If I say kindly find out the order for the electron density. So what happens is I take a case of A negative, then is A, and then is A positive. Okay. As I've already told you, the one which is gaining electrons carries a negative charge. The one which is losing electrons is carrying a positive charge. So if I ask you, whosoever is having electron density more, kindly tell me. So you will say, ma'am, the person which is gaining negative charge will have more electrons because it is gaining electrons. So it is acquiring negative charge. And the atom which is losing electron basically acquires what charge? Positive, because the electrons are being moved far away from that atom. That means here electron density is very less. This is neutral, and this one is the case in which electron density is more because it is gaining electron. So the electron density order is going to be this. Now this will also help you in the coming part. So this is all about, the general concept that you need to keep in your mind. Other than this, as you have seen, I have already done one case of the polarization of sigma electrons. I want you people to put arrows, learn to put arrows in which direction. Now see over here, I'm taking this case again, carbon, 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 and fluorine. I have this case with me, right? This was the single case, but now what different I'm going to do over here is I'm going to add 2 more fluorine atoms over here. Now kindly, first of all, put the charges over here. Secondly, try to put the arrows. Now, if I want you to put charges over here, what you will do is you will say, ma'am, fluorine is more electronegative, so it will acquire partial negative charge, and carbon will acquire partial positive charge. Fluorine is more electronegative, so partial negative, right? Now what happens over here, students? If fluorine is more electronegative, it is attracting electron towards itself, so the arrow will be in this direction towards fluorine. Learn to use arrow, it is going to help you a lot. Okay, it is gaining, or a pull of electrons is moving towards fluorine, so the arrow is moving towards fluorine. Now in this case also, an arrow is moving in this direction towards fluorine, an arrow is moving in this direction towards fluorine. Now what happens over here? Now when there is a group of fluorine atoms, when I've kept over here, what do you observe? This carbon is now electron deficient, and due to 3 fluorine atoms, it is feeling more electron deficient, so it requires some kind of electron to stable itself. What does it do? It will take some electrons from the next carbon which is attached to it, so it will take some electrons from here, and hence when it is giving electrons to this, it will acquire what? Double partial charge. Now why does double partial charges occur? Because the first carbon was making a bond with fluorine atom, which was more electronegative. So the electrons from the first carbon are moving towards fluorine. So both of these charges has a partial positive or a partial negative charge. But when I talk about the next carbon atoms, then these will acquire double partial charge. Now if I talk about the third carbon atom, as it has gained some electrons from this carbon, now this carbon is electron deficient, it will acquire what? It will acquire some charges from the another one. So it will acquire triple partial charge, positive charge. Now again, this is now electron deficient, it will take more charge over here, it will acquire 4 times partial positive charge. Now ma'am, you are taking all the charges to stable the another carbon. Till when this process will carry on? So it is up to only 4 carbon atoms, not more than 4 carbon atoms. This process is carried forward. Clear? So you need to keep in your mind, first of all, how to make charges, how to develop charges over here. Another point you have to keep in your mind, that how to use the arrow, in which direction arrow is kept. Whosoever has more electronegative or whosoever gains electron, the arrow moves in that direction. This was the basic knowledge that we require in the upcoming topics. Now the very first topic that we are going to start in the electronic displacement is inductive effect. As I've already told you, inductive effect basically is a kind of permanent effect. Inductive effect is a kind of permanent effect. It is represented by capital I. It is represented by capital I. Now, what do you mean by inductive effect? Here, it is distance dependent permanent effect. Okay, so first of all, it is permanent effect. Second thing, it is distance dependent. It is distance dependent. That means it depends upon the distance, as we have already seen in the previous case when there was carbon, carbon and fluorine. It was moving till the fourth carbon atom, right? Okay, now it can be neglected after 3 or 4 carbon atoms. After 3 or 4 you can neglect this effect, so it can be neglected, after 3 or 4 carbon atoms. Clear, students? Now let us talk about the inductive effect in such a way, which we have already discussed. But to give an example over here, the very first example arises as of carbon, 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 carbon and fluorine. This we have already discussed, students. Now, my question arises, why does here the polarization of sigma electron takes place? Now the answer is due to the difference in electronegativity. Here, due to difference in electronegativity, polarization of sigma electrons occurs, due to which they acquire partial positive or partial negative charge. This will acquire partial negative, this will acquire partial positive, this will acquire double partial positive, this will acquire triple partial positive. Now to make arrows, we know that it is giving electrons, you know, the pull is towards fluorine. Now the pull is towards this carbon because it is electron deficient and it needs electrons. Pull is over here, right? So this was the usage of arrow, and this is the concept that we are going to use. In other words, if I would define inductive effect, all I would say is that here the polarization of electrons, sigma electrons, takes place. Clear, students? Now if I talk about this case, I want you all to do what? You all to kindly mention the charges, and the next thing is to kindly mention the arrows. How to use the arrows? I want you all to mention the arrows. Now see, in this case, we know that it is a bond line notation. It contains carbon, carbon, carbon atom all over here, right? And we have this oxygen atom over here. It is basically a hetero atom, right? So we have this oxygen in between these carbon. Now what happens over here, as I've already told you in the general knowledge which we have discussed over here, the concept of electronegativity. Oxygen is more electronegative than carbon. If oxygen is more electronegative than carbon, then it has a tendency to attract the shared pair of electron towards itself. Now if it has the tendency to attract shared pair of electrons, electrons will move in this direction, it will move in this direction. Now this first carbon, both of these carbons are electron deficient, so they want electrons to be stable. Now they will gain some electrons from this carbon. Now the arrow will move in this direction. Now what happens? These two second carbons are now electron deficient. They want more electrons to be attracted towards them to become stable. Now the electrons will move in this direction. You know? So this is what? This is the usage of arrow that you need to understand over here. Now what happens over here? Here minus I effect comes. Now what I'm talking about minus I, ma'am, we don't know about this concept. What is minus I? Till now we have just studied what is inductive effect. Now a certain term I want you all to understand is that inductive effect is further categorized into two types, which we are going to see. It's just I'm going to tell you with the help of examples. Here just I want you people to make arrows. If you learn how to use arrows, how to make charges, then it is easy for you. Now let us make charge over here. If I say it acquires electrons, it is a partial negative charge arises over here, and this carbon, you know, it basically, you know, get aparts from the electron. There is a distance between the electrons. Now it will acquire what? It will acquire partial positive charge. This is the first carbon, so this will also acquire partial positive charge. If I talk about the second carbon atoms, now these are again giving, you know, they are aparting from the electrons because the first carbon atom needs electrons. So here it will acquire double partial positive charge. It will acquire double partial positive charge. Clear? Now here if I talk in this case, it is a kind of a different concept. If you see, if you talk about OH, here is oxygen, right? But here is O negative. There is a difference between both of these. Here is oxygen, and you know that carbon is less electronegative than oxygen. So if carbon is here, according to the bond line notation, so I would say carbon is less electronegative, so towards oxygen the electrons will move like this. Like this carbon is there is a shift of electron towards oxygen. Now it is electron deficient, so it is gaining electron from both of the ends. Now if I talk about O negative, as I've already told you in the general knowledge concept, that when you are having A negative, A or A positive, in three of these cases, which has more electron density, I've already discussed with you, this will have more electron density than this, right? So here what we are observing, that A negative basically is having more electron density, and if someone is having more electron density, it will donate its electrons. So what happens over here, now this O negative, students, this O negative will donate its electron to carbon, because it has more electron density. So the direction over here is this, and over here is this, because this carbon is also donating to this carbon. So it is a different kind of thing that you're observing over here. In one is OH, which is having a pull of electron towards here, and one is O negative, which is giving electrons pull towards carbon atom, because it already has more electron density. Clear? Now let us see this case. Here is simple OH, so I would say carbon is less electronegative than oxygen, so oxygen will have a pull of electron towards itself, will gain partial negative charge, this will gain partial positive charge. Hence this carbon is now electron deficient, so it will take a pull of electron from the another carbon, so will carry out the double partial positive charge, and the third one will carry triple partial positive charge. So now you are being able to put the arrows, and which is all required for the upcoming concept. Now comes this case. If I talk about this case, what happens, we know that this is basically the bond line notation. Here carbon, 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 carbon will come, right? If I talk in detail, I would say nitrogen is more electronegative than carbon. Hence, nitrogen has the tendency to attract the shared pair of electron towards itself. Now, if nitrogen has this tendency, this will attract. Okay, now this carbon is electron deficient because it has given some part of electrons, because it is a far more distance from the electrons which it was sharing equally. Now it is at a far more distance, so it is electron deficient. It requires electrons, so it will take the electrons from the another carbon, and they will take from the another carbon, and further they will also take from the another carbon. So this is going to be the arrow making here in this concept, right? Now if I talk about this case we have already done twice. We have done this case. This I'm going to represent in such a way, and you will see, yes ma'am, we have already done. If I'm going to open up this CF3, it is same which we have already covered. It is the same thing, right? So no need to do this again and again, because you already know this. Now I have used here 5 carbon atoms, you can use 3 carbon atoms, it is the same thing, so no need to worry about it. Okay, because this concept is is valid up to 3 carbon atoms. So if you are going to write 4 carbon atoms or 5 carbon atoms, so that doesn't make sense, because it will be valid up to only 3 or 4 carbon atoms. Clear, students? Okay, now moving to the types of inductive effect, all I would say is inductive effect basically is of two types. One is plus I effect, another one is minus I effect. Now, what is plus I effect and what is minus I effect? To understand plus I and minus I, we need to understand the standard concept through with the help of which we define plus I and minus I. See what happens whenever you go in market, whenever you go to buy bananas, what do? You see there is a standard unit kept, that is dozen, right? So you know what is a dozen. So there is a standard kept. If you want this much banana, then you measure in the dozens. Now if I want to measure plus I and minus I effect, what I'm going to do, I'm going to keep a standard with the help of which I'm going to differentiate or compare the other effects, so that I could be able to define what is plus I effect or what is minus I effect. So the standard that is kept over here is simple. When there is carbon, 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 and hydrogen. So when you observe there is a bond between carbon and hydrogen, here we see that when there is same atom, when there is all carbon atoms, we say there is no polarization of electron. But when we see here that carbon and hydrogen comes, you will say that, ma'am, here we have seen the general knowledge concept, we have seen that hydrogen is less electronegative. So you don't have to apply that concept over here, because here this is considered that it has an inductive effect of 0. That means it is kept as in standard. It is kept as a standard over here, that here inductive effect is 0, and the bond present in between these sigma pi electrons are basically A. Let us say they are A. Let us say they are A. Now we are going to compare the with this A bond the other two. Now first of all, we are going to see the plus I effect. And if I talk about the minus I effect, Okay. Now, what I have used over here I used hydrogen, which was kept as a standard. Now, for both of these cases to understand, one I have taken is Y group, another one I've taken is Z group. If I talk that A is basically less than C. Now, what is C over here? C is this bond, the bond between these two, where the electronegativity difference arises. Now, as I said, A is less than C. Then we observe plus I effect. Now, what happens over here? There is an electronegativity difference over here. See, this carbon and Y has electronegativity difference. This carbon and Z has electronegativity difference. We are keeping this as standard where is no electronegativity difference. Here, electronegativity difference arises. Here, what happens? Here, when I am saying A is less than C, that means it is electron donating group. Kindly listen to me very carefully. It is electron donating group. That means this Y which you are going to use will donate electrons to these. So it is electron donating group. This one is electron donating group. This C is more than this A. If it is more than A, that means it has more electronegative. It is more electronegative, so it will donate. Clear? Now, if I talk about this case, what do you observe over here? Let us say there is a bond B here, okay? And all I would say that A is more than B. If A is more than B, what do we observe over here? It is electron withdrawing group. Now, what do you mean by electron withdrawing group? Which withdraws electron, which takes over the electrons. Now, this Z will take the electrons from the carbon atoms. Hence, it is electron withdrawing group. Hence, it is minus I. In other words, if you're not getting this, what is A, what is C? Just understand that plus I is the one which is electron donating and minus I is the one which is electron withdrawing. Clear? Okay, students. Now, I would take some of the cases and we will understand basically where does plus I effect occurs, where does minus I effect occurs. So the very simple case that I would take first over here is CH3, CH2, CH2, CH3. Kindly tell me which kind of effect do you observe over here, plus I or minus I. So I guess all of you have done this because here you are seeing only two kind of atoms. One is carbon, another one is hydrogen. And we have seen that we have kept carbon and hydrogen as a standard reference. So if it is kept as a standard reference, it will be what? It will be a non-polar molecule because there is no polarization occurring. So there is no polarization of charges. No polarization of sigma electrons. Hence, it is what? It is non-polar. It is what? Non-polar. Non-polar is the one in which there is no poles, no positive, negative poles arises, right? Now, let us take one more case. CH3, CH. Okay. Now, if I take this case, CH3, CH2, CH double bond, CH2. Kindly tell me which kind of effect do you observe? Minus I or plus I? First of all, what we need to check? We need to check, ma'am, electronegativity over here. How to check electronegativity? See, this carbon. Kindly tell me the hybridization for this carbon. Now, how to check hybridization? To check hybridization, we should see the number of sigma bonds and the lone pairs. Pi bonds are not counted in hybridization. So there is one sigma bond over here, one over here, and one with hydrogen. Pi bond is not counted. How many sigma bonds? 3. And for 3, let me tell you, if the sum of sigma and lone pair comes out to be 4, hybridization is sp3. If the sum comes out to be 3, hybridization is sp2. If the sum comes out to be 2, the hybridization is sp. This is the basic concept, right? So here, if I talk about this carbon, it is making 3 bonds, 3 sigma bonds. There is no lone pair. There is one pi bond, but pi bond is not counted in hybridization. So it is making 3 bonds. Hence, hybridization is sp2. Now, if I talk about this carbon through which it is bonded, it is bonded with this carbon, it is bonded with this carbon. If I talk about this carbon, it is also sp2 hybridized. So these are same thing, but what is different over here? This carbon which is bonded directly with the sp2. This carbon is what? It is making 2 bonds over here and 2 with hydrogen. That means total 4 sigma bonds are being made. Now when 4 sigma bonds are being made, students, what would be the hybridization? It would be sp3, ma'am. Now see. I've already told you percentage S character is directly proportional to electronegativity. What I've told you, percentage S character is directly proportional to electronegativity. Sp will have more electronegativity than sp2, and then comes sp3. I hope so you remember this in the general knowledge concept. So now, which will have more electronegativity? Ma'am, sp2 will have. That means this two carbons will have more electronegativity. This will have what? This will have more electronegativity. So which kind of effect it is? If it has more electronegativity means that tendency to attract shared pair of electron. That means it wants some electrons. So it is a kind of what? It is a kind of electron withdrawing group. Now, if it is a kind of electron withdrawing group, so it shows which effect? It shows minus I effect. It shows which effect? Minus I effect. We have seen in the previous case. See, electron withdrawing group is this one, which is minus I. Electron donating is the one which is 1 plus I, right? Now, over here, on this case only, let us see one more case. One more case is still left over here. So, we will see the other case that is left is of triple bond. Let us see of triple bond. If I talk about triple bond, CH3C triple bond CH. Now again, I want you all to apply this case over here, find out the hybridization. If you find out the hybridization of the carbon atoms over here, you would say that this carbon is basically making 2 sigma bonds, other 2 are the pi bonds. So if they are making 2 sigma bonds, the hybridization is going to be sp. And if I talk about this carbon atom, again it is going to be sp because it is making 1 sigma bond over here, and another one will be the with hydrogen. If I talk about this carbon atom, it is making 4 bonds. That means it is sp3 hybridized. So this 2 are sp, while this one is sp3. Which will have more electronegativity? Again, sp will have more electronegativity. Now if this has more electronegativity, that means they require electron, they want electron to be shifted towards them. Now that means they are electron withdrawing group. That means it shows minus I effect. It shows which effect? It will show minus I effect. Hope so it is clear to you people. Now students, coming to the important concept, that is the order of plus I group. Now we have seen inductive effect. What is inductive effect? Let us revise it. It is distance dependent effect which basically is seen up to 3 or 4 carbon atoms. It is permanent effect. It is delocalization of sigma electrons, right? This was inductive effect. Now, the second thing that we understood was about the types of effect. In between, we got a lot of general knowledge about the organic chemistry, right? Now, here comes the order of I groups. Plus I group or minus I group. Whenever you are being given some question, they will ask you which is more stable. So how you are going to tell which is more stable? If you remember this order, it will help you to do questions even very fastly, right? So students, if you see the very first case over here, you see whenever you are going to see CH2 negative group. Now what does happen over here? CH2 negative here is, here it will have more donation. Now if it will have more donation, as I know, electron donating group is what? It will show plus I. So this will show plus I more because it is more electron donating. Then comes this NH negative, then comes O negative. As you have seen the case of O negative previously, when I was given OH and O negative in the case when I told you to make arrows, right? So O negative was donating its electrons to whom? It was donating its electrons to carbon. Now why it was donating its electron to carbon? Because it had electron density more. The ones which will have electron density more will donate. The ones which do not have electron density more or which are electronegativity, who require electrons, who are electron withdrawing, will have minus I. But who already has electron density more, don't get confused between electron negativity and electron density. Both are different concept. Electron density is the one in which we have seen that whosoever has electron density more will give its electrons to the another one. But whosoever has more electronegativity, they will have the tendency to attract electron towards itself. Clear? So here, as I told you, this will donate electron. If this will donate electron, that means it is less electronegative. That means it is less electronegative. Now don't compare this with electron density concept. Okay, now if I talk about this NH negative, this is O negative. O negative, we have already seen that A negative A and A positive. What I told you this will have more electron density than this, than this. That means if I'm talking about plus I group, all I want is first the negative charge is 1. Why the negative charge is 1? Because the negative charge is 1 have more electron density. Now if these have more electron density, it will donate. Now if they will donate, they will have plus I group. So you will see what? You will see an order where first minus negative charges comes. In plus I order, always remember, first of all, the first order that you're going to observe is of negative. Why? Because they have more electron density, and more electron density means they will what? They will donate, and if they will donate, then they will have plus I group. Then after the students, what happened? There is a, you can see 3 degree, 2 degree, 1 degree over here. So here what do you observe? Again in this case, here you can see they are what? They are electron donating. They will donate its electron to this carbon. They will donate, they will donate, they will donate. Here 2 will donate, here only a single one will donate, here nobody will donate. So what do you see? Here this will donate to the group that is being attached. So what do you observe here? These 3 are donating to the group. Now here 2 are donating, here only 1 is donating, here only, here only this one is donating to this, and here this is donating to the group. So what do we observe? When more are donating, it will have more I effect. When less are donating, they will have less effect. So 3 degree, then 2 degree, then 1 degree, and simple then is methyl group. Other than this, what do we observe? This is tertiary. This is, you can see this deuterium. Sorry, if I will say this is tritium, deuterium and protium, not tertiary. I got confused in this tertiary, secondary. Okay, don't get confused in this. This is tritium, deuterium and protium. In this case, students, what happens? We know that these are isotopes. They will have same atomic number, but what is the difference over here? Atomic mass is the difference over here. So whosoever is having higher atomic mass will donate more. Now if they will donate more, they will show plus I group. So these you have to learn. First order, I guess you have to learn. It is quite simple. But this you don't have to learn, because 3 degree is more stable than 2 degree, then 1 degree. It is quite easily we get in our minds, right? Other than this is also very easy. Why this is easy? Because if they're isotopes, then you need to keep the atomic mass in your mind. More the atomic mass, more will be the donation, more will be the donation, more will be the plus I group. Clear? Okay. Now, similarly, we see the order of minus I group. Now, if I talk about the minus I group, this is the order. Now, first of all, see the difference. In the previous case, we all saw the first groups contain the negative charges. Here, all these groups contain the positive charges. Again, I am repeating the same concept. If you are given A negative, if you are given A positive, or if you are given A, which will have more electron density? A negative. Which will have less electron density? This. The one which is having less electron density, not negativity, electron density less, will what? Will withdraw its electron. When it is withdrawing electrons to make it electron density more, it is known as minus I group. So the positive one will withdraw the electrons, hence the positive ones are written first, right? So now there is an order of OR2 positive, OH2 positive. Now this is the exception over here, just you need to keep in your mind, right? Then comes NHR2, and then comes NH2R positive. Now comes the second the order. This order lies in this way. Firstly you will write, then secondly, then thirdly, then fourthly. This basically you can write in one single horizontal line also. Clear? Now if I talk about the second one, we have NO2, then we have SO3H, then we have CN cyanide. If I come across the next one, then we have this group COH, C double bond OH, then we have C double bond CH3, then we have C double bond OH carboxylic group, then we have C double bond O OR. Then comes this one. It is quite different and it is quite important also. This you have to keep in your mind. For minus I effect, fluorine has more minus I, then chlorine, then bromine, then iodine. Kindly put a star over here. This you are going to observe in many of the cases. In many of the cases. So put a star over here. Now if I talk about the last one, this is the last one. This is also again the exception over here. Okay. Now this order you need to keep in your mind. Don't, don't keep on writing and learning this. No. Just read it once, twice and thrice. That's it. When you're going to apply this in questions, you will automatically get to know. You'll compare and learn. You'll compare, this is plus I group, this is minus I group. And how you are going to compare? You're going to compare with the concept of electron donating and electron withdrawing. And that will only be learnt when you are going to practice more and more questions. Clear? So students, this was all about the order of plus I and minus I. Now there are some questions of order. First of all, if I talk about this order over here, we have this. Now what do you observe over here? We observe that, ma'am, the central atom over here is nitrogen, over here is also nitrogen. This contains what? It contains R group, alkyl group, while this contains hydrogen. This contains hydrogen. Ma'am, we know that. What we know over here is that we have to tell the order, which order it follows. Does it follow minus I or plus I? First we need to identify this. Plus I is the one which is electron donating, minus I is the one which is electron withdrawing. Now what happens over here? We know that R group refers to CH3 or CH2CH3. We have seen the order of 3 degree, 2 degree, 1 degree. They all were what? They all were, what they were doing? Basically what they were doing, they were seen in the plus I effect, right? But here what we are saying, these R groups are attached with nitrogen. These are attached with nitrogen and it has positive charge over here. Now this N positive is attached with hydrogens over here. This is attached with hydrogen. Now what we see that this will have minus I more than this. This will have minus I concept more than this. Minus I, that means electron withdrawing more than this, because they will withdraw electrons more as comparative to this, because hydrogen is least electron negative, than nitrogen. That's why. If I talk about this case in which we see that centralmost atoms are different, here centralmost atom is different. Here is nitrogen, here is phosphorus, here is arsenic. So what do we observe over here? We know that percentage S character is directly proportional to electronegativity. So the deciding factor over here is the central atom, because other than the central atom, all acquire the R group. When all acquire the R group, we know that percentage S character is directly proportional to electronegativity, right? And other than this, we know that the deciding factor is what? Deciding factor is our central atom. Now here, whosoever will have more electronegativity, kindly listen to this, whosoever will have more electronegativity will have minus I effect. We have seen in this case, nitrogen is having what? More electronegativity than carbon. So if it has more electronegativity refers to as tendency to attract refers to as electron withdrawing refers to as minus I effect. Electron withdrawing refers to as minus I. That means the person that is going to have more electronegativity is minus I, because it will attract, it will withdraw. Now who will withdraw? Which will have more electronegativity? Now in this case, who have more electronegativity? Students, nitrogen. Now if it has more electronegativity, the order is going to be this. Hope so it is clear to you. Now students, comes the application of inductive effect. Now if I talk about the application portion, all I would say, in the application we are going to see the stability of the reactive intermediates. What we are going to observe over here is the stability of reactive intermediates. Other than this, students, we study about acidity, basicity. This is all in the application portion. Other than this, you understand about dipole moment, melting point, boiling point, dipole moment, melting point, boiling point. Okay, other than this, students, what do you see here? You see the stability, or you can see the reactivity of alcohol, carboxylic acid. Okay, now students, these were the applications of inductive effect. One by one, I'm going to explain you in detail. If I talk about the first application, before that, I want you all to understand one more concept of general knowledge. Now, what is the concept that we are going to understand over here? That is about bond breaking. That is about bond breaking concept. Now, what do you mean by bond breaking, ma'am? Okay, see, bond breaking, students, can be of two types. It can be of two types. Now, what are the two types we define bond breaking into? If I talk, when there are same atoms given to you. Okay, see, when students, you are given A bonded with A. This is the first case, and the second case is going to be when A is bonded with B. Now you are given two cases when the atoms are same and when the atoms are not same. When the atoms are same, does electronegativity difference arises over here? No. Why? Because there are same atoms. So there is no difference in electronegativity. No difference in electronegativity. When there is no difference in electronegativity, that means delta En is going to be 0. Now when there is delta En is going to be 0, that means there is no electronegativity difference. That means electrons are present in between. They are not shifted towards this more or that more. No, they are present in between. Now which kind of breaking arises over here? I say electrons are present in the centermost position like this. Now one thing you need to keep in your mind, when they are sharing equal electrons, then bond cleavage occurs over here in such a way. Now what is this arrow? See, when I am representing this arrow, it is refers to as 1 electron. When I am representing this full arrow, it is referred to as 2 electrons. Now you should learn the movement of arrows also. We have seen the arrows of electronegativity. These are a kind of different arrows. Now students, if I am talking about this arrow, it refers to as the movement of one electron towards this A and one electron towards this A. We know that a single bond contains two electrons. When we are doing a breakage of bond, that means we are dividing this bond into such a way that AA gets separate. Now if AA are getting separate, both of the atoms are same, that means electronegativity difference is not there, so both of them will acquire one electron, and when they acquire one electron, we show this one electron by this arrow. Now what will arise over here? A radical plus A radical. Now this radical, this dot is referred to as one electron. So this kind of cleavage, when we see same kind of atoms are present, it is known as homolytic cleavage or homolytic bond breakage. This is the very first kind, which is homolytic cleavage or homolytic bond breaking, students. Kindly put this in a box. Now this was also a general concept that you need to keep in your mind. Now comes the next case. If I talk about this case, I want this bond to be broken. Now here what do we observe? Here we observe basically the electronegativity difference, because there are different atoms. So yes, it is but obvious there is an electronegativity difference. Now if I say there is an electronegativity difference, why? Because atoms are different. Atoms are different. Now if students atoms are different, and if I say let us assume B is more electronegative than A, what happens over here? If B is more electronegative than A, so here A will acquire positive charge and B will acquire negative charge. Now this kind of cleavage is known as heterolytic cleavage. This kind of cleavage is known as heterolytic cleavage. Now what is heterolytic cleavage? When two different atoms are present and the bond breaking process occur. When same atoms are present and the bond breaking occurs, that is homolytic. When two different atoms are present and due to the electronegativity bond breakage arises, that is heterolytic cleavage. Now students, comes our first application, that is stability of a reaction intermediate. Stability of, this is the application portion of reaction intermediate. Now, as I've told you in the very first slides, that what were reaction intermediates? They were carbocations, they were carbanions, they were carbon-free radical. We have understood this. Now here, if I talk about the stability, we observe the stability in the case of carbocations as well as the carbanions. So what kind of stability do we observe? If I talk about carbocations, the second one is carbanions. First of all, we need to understand what are carbocations, students. Carbocations, if I split it into two types, it is carbon plus positively charged species. It is what? It is carbon plus cations refers to positively charged species. positively charged species. Now, if I talk about carboanions, it is again what? Carbon plus negatively charged species. Negatively charged species. Now see, if I talk about carbocation in detail, they are also known as carbonium ion. They're also called carbonium ion. Also called carbonium ion. Clear? Now students, if I talk about carbocation in detail, let us take an example. How does carbocations are formed? If I take a general example, I would say, for example, if I have CH3F. Now we know that carbon is bonded with fluorine and we know that fluorine is more electronegative than carbon. Now what does occur over here? Heterolytic cleavage, we get CH3 positive and F negative. Why? Because there is a difference of electronegativity over here. Difference of electronegativity occurs here. Heterolytic cleavage occurs as fluorine is more electronegative than carbon. So fluorine acquires partial negative charge and carbon acquires partial positive charge. So again, carbon plus positively charged species. That means here CH3 is what? Here this CH3 is what? Here this CH3 is carbocation. Here this is carbocation, students. Now what? Carbocation is basically what? Here we are seeing heterolytic cleavage. And how is the structure of carbocation? Basically it is electron deficient species. How I would say it is electron deficient? If I talk about its structure over here, let us see. This is carbon. Okay, now this is hydrogen. I have this is hydrogen, this is hydrogen, and this we have the positive charge over here. Now this is the structure for carbocation. This is the structure for carbocation. It is electron deficient species. It is electron deficient species. Kindly put a line over here so that we don't get confused between carbocation and carbonion. We don't get mixed both of these, right? Okay. Okay, students. So now you can see carbonion we'll discuss in the next slide. In this slide is all I'm telling about carbocation. This is a structure for carbocation. It is electron deficient species. How many electrons are present over here? You can see that here basically there are 6 electrons present. It is sp2 hybridized, students, and it is trigonal planar. It is trigonal planar. sp2 hybridized with 6 electrons because it is electron deficient, hence it is 6 electron species. Now who will attack over this? As it is electron deficient species, nucleophile will attack over this because nucleophile will have more electron density. Now coming towards what? Carbonion. This was all about carbocation, which is the one which is having positively charged species, also known as carbonium ion. Now if I talk about what? If I talk about carbonion, this is again carbon plus negatively charged species. Negatively charged species. This is what is carbonion. Now if I talk about carbonion, let us take one case like I took CH3F. Here let us say CH3Z. Now I would say that this Z has less electronegativity than carbon. Now, if it has less electronegative than carbon, what do we acquire over here? Again, heterolytic cleavage, because there is a difference in the electronegativity. Carbon has now more electronegativity than the Z group. So, if it has more electronegativity, then we have CH3 negative plus we will have Z positive with us. Clear, students? Now, what is CH3 negative over here? This CH3 negative is carbonion. This is carbonion. Now let us talk about its structure. So how does it looks? It looks like this. This is the structure for carbonion, which is basically what? Which is basically tetrahedral. Now if you count the electrons 1, 2, 3, 4, 5, 6 and you have 7, 8 electrons, it is electron rich species. It has electrons, 8 electrons. It is electron Rich species. So who will attack over here? Electrophile will attack over here. Don't get confused about nucleophile, electrophile. We will cover in the upcoming topic. So just I want you to understand the difference between carbocation and carboanion. Okay. Now if I talk about the carbocation, the order of carbocation, the stability, because we have seen the plus I effect basically defines us about the carbocations. We have seen this case CH3 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 positive. Then we saw this case CH again is CH3 again is CH3 positive. Then we have CH CH3 and the last one is CH positive. Now for these carbocations which will be more stable, we have already seen this case, students. We have already understood this case. How we have understood this case? If I talk over here, I would say the order is going to be this. You remember plus I effect. In plus I effect, what I told you this order to remember. So these were carbocations. This is 3-degree carbocation, then 2-degree, then 1-degree. You need to remember in your minds that 3-degree carbocation is more stable than 2-degree, then 1-degree. This I am talking about carbocations, not carboanions. Don't get confused. Now, if I talk about a ring-like structure, this was the first case that you need to remember. Okay, now students, for example, if you have this kind of structure which will have more, stability for this carbocation. So I would say the small ring will have more minus I. The small ring will have more minus I. Now, if it has more minus I, that means the larger ring will have the plus I effect. So this is going to be the order. This is going to be the order. Other than this, whenever you are giving any of the compound, kindly find out if it is 3-degree, if it is 2-degree or 1-degree. If it is 3-degree, it will be stable, then 2, then 1. This is a general case. Other than this, you can get many cases, but you need to find 3-degree, 2-degree, 1-degree. That will be your answer, right? Now, students, if I talk about the next for the carboanions. If I talk about carboanions, the order is 1-degree is more stable than 2-degree and then 3-degree. For carbocations, what do we observe? We observe that 3-degree was more stable than 2-degree than 1-degree. Here, 1-degree is more stable than 2-degree than 3-degree. Now let us make the structure for these also. This is our 3-degree. It acquires negative charge. Then is our 2-degree. And then is 1-degree. So 1-degree is going to be more stable than 2, then the 3-degree. If I talk about the ring-like structures over here in this was the first case. So as I've already told you, for carbonine, the small rings one will be more stable. So this is going to be the structure. This is going to be the order. Now for carbocations, the larger rings were stable, not the smaller ones. For this, smaller ones will be stable than the larger one. Other than this, if you acquire any question, kindly find out 1-degree, 2-degree, 3-degree. Then apply this concept. 1-degree will be more stable for the case of carbonine, then 2-degree, then 3-degree. Now comes, students, our next topic, that is the reactivity of alcohol. This is also one kind of application in inductive effect. For the reactivity of alcohol, what kind of questions arise over here is acidic strength. What arises over here is acidic strength. They ask you about acidic strength. So when they ask you about acidic strength, see, you know two kinds of effect. One is minus I, one is plus I. Whenever you need to find acidic strength of any of the alcohol, acidic strength is directly proportional to minus I groups. Those who are having minus I groups will have more acidic strength. And the one which will have the plus I group, they will have less, because acidic strength is inversely proportional to plus I but directly proportional to minus I. So this is the order that you need to keep in your mind. Okay, this is the first order that you need to keep in your mind. And whenever you have calculated acidic strength, do remember acidic strength, if acidic strength is more, then more H positives are produced. more H positives are produced. And if more H positives are produced, then pH is going to decrease. Less will be the pH. More will be the H positive, less will be the pH. More will be the Ka, more will be the Ka, less will be the pKa. Less will be the pKa. So this is all what you need to remember in the reactivity of alcohol, students. Now coming to the next rule that you need to keep in your mind is DNP rule. Next is rule that you will see in the questions, that is DNP rule. Other than this reactivities. Now what do you mean by D? D is distance, N is number, and P is power. P is power. So the order comes in this direction only. First of all, you will see distance, then you will see number, then you will see power. If I talk about comparing one question, if I give you question over here, compare acidic strength. Compare acidic strength, and if I give you one single case in which for alcohols only, for example, I'm giving you okay. Now students, this is the question which I have given you. This is your A, this is your B. Now kindly tell me which will have more acidic strength. You will say, ma'am, first of all we need to see D distance. Distance refers to at what distance of the group is the another group lied. See, OH is present over here, so Cl is lied after one carbon to the other carbon. So distance is equal for both of the case. Here is OH, here is OH. Then comes one carbon, then comes carbon, then comes carbon. It have fluorine, it have two chlorines, right? So distance is same. Distance is same over here. Now, let us talk about what? Talk about number. How many fluorine atom? One fluorine atom. How many chlorine atom? Two chlorine atom. How many? Two. You know, fluorine, chlorine, bromine had which group? Minus I group. So this is minus I group. We know that. Even chlorine will have minus I. But we are talking about number. How many? Here is one, here is two. Which have more? This has more. So the acidic strength is this. It does not depend that fluorine will have minus I more. No. First of all, check distance, then check number. If number is same, then move towards the power. Power refers to as plus I minus I. Clear? So first of all, check distance, then check number, then check this, that this has more I. If they had same number, no students, if they had one chlorine and one fluorine, then this would be correct because fluorine has more minus I, right? But first of all distance, then comes number. Here is two chlorine, here is one fluorine, so it will be preferred, right? Now if I talk about one more case, let us talk about acidic strength for carboxylic acid. Do remember one more thing. In the previous case, I have already told you here this order. If they'll ask you H positive order, pH order, Ka order, pK order, kindly calculate acidic strength. H positive will have same order. pH will have the opposite order because it decreases. K will have the same order and pK will have the opposite order. Clear? Now coming back to this question of the carboxylic acid, I have now two groups with me. For example, I say you here is cyanide group. Here is methyl group. Methyl, or I would say CH3. Methyl is basically CH3, but I'll write directly, right? Now students, again what we are going to apply over here, we are going to apply the DNP rule. First of all, check the distance from the carboxylic acid. After one carbon to the another carbon, it is CN. After one carbon to the another carbon, it is CH3. Distance is same. Distance is same. Now come towards number. 1 CN, 1 CH3. Same. Again, now here number is also same. 1 CN, 1 is, one is CH3. Now, remember, CH3 has which group? CH3 has which group? It has plus I group. And CN has what? Minus I group. Hai na? So here, acidic strength, we know that acidic strength is directly proportion to minus I and inversely proportion to plus I. So minus I will have more acidic strength. Clear? As you know, CN has minus I. Hai na? That's why. Clear, students? So in such kind of situations, you can do the acidic strength. You can calculate the acidic strength. Other than this, basicity question arises. So basically, basicity for gaseous phase is directly proportional to plus I groups. Acidity is inversely proportional to plus I group, acidic strength, but basicity is directly proportional to plus I groups. Okay, students, now comes the stability of carbocations. If I talk about stability of carbocations, I'll write 3 of the cases over here. Then comes the stability of carboanions. And then comes the stability of free radical. So if I talk about all of 4 of these cases, see, if I talk about stability of carbocation, stability is directly proportional to plus I group. Here, for carbocation, stability is directly proportional to plus I and inversely proportional to, and inversely proportional to minus I. If I talk about carbocation, it is the opposite order. It is the opposite order. Stability is directly proportional to minus I and inversely proportional to plus I. Now, if I talk about stability of free radical, now what is free radical? Carbon containing 1 electron. This is free radical. Now, if I talk about this, it is same as that of carbocation. The order is same. This one. Same as of carbocation. Clear, students? So here you have seen the application portion of inductive effect. This was the very first effect, permanent effect under the category of what? Electronic displacement. Now we will move forward towards our next kind of effect, that is resonance effect or mesomeric effect. But before understanding resonance effect or mesomeric effect, we need to understand what do you mean by resonance. So students, as we were understanding about resonance, first of all I would love to tell you that if we need to understand mesomeric effect, first we need to understand about resonance. Then we will move forward towards the mesomeric effect and we will understand the difference between them. Now, what is resonance? To understand resonance, there were 2 definitions. One were the old definition and one was the new definition. According to the old definition, what do we observe? We observed that basically what happened. Basically, let us take an example, and with the help of that example, I'm going to explain you the definitions also. See, if I talk about O3 molecule, if I talk about O3 molecule, which looks like this. Okay, now students, in your notebooks, you have seen this structure. You have already drawn also this structure. But is it the actual structure of O3 molecule? So the answer is no, a big no. This is not the actual structure. Why it is not the actual or the real structure? Because if I talk about resonance also, in resonance, what do we observe? Why does resonance arises? When a single structure, like this is a single structure, it cannot explain the whole property of the molecule, O3 molecule. Then we require a different kind of structures similar to this, Now, these structures which will explain the property of resonance, these structures are referred to as resonating structures. So, we will make the resonating structures until when? Till we get all the properties of the compound, of the molecule. So, this basically single structure is unable to define or to, express the properties of the molecule O3. So, we require more structures. And so, this is not the real. How does the real structure look like? The real structure basically looks like this. Now, what is this? See, if I talk about this structure, practically what is single bond is basically the longer bond and double bond is basically the shorter bond. But as I told you, it cannot explain the whole property. The real molecule is this one. This real molecule is resonance hybrid. This real molecule is a resonance hybrid which have all the bonds equal in length. And why does this happen? Why does this happen that all the bonds in this are equal in length? Due to the delocalization of pi electrons in the conjugated system. In the conjugated system. Due to this delocalization process, students, these bond lengths came to be equal. And so this structure is not the real one, because here if you observe, one is longer, another one is shorter, and we see that this is a kind of resonating structure, not the complete structure, not the exact structure. The exact structure basically looks like this. We will understand how to make resonating structure, how to make resonating hybrid in the coming topics. But first of all, we need to understand that why there is a requirement of resonance. Resonance was required in order to explain or to express all the properties of the molecule. Clear? Now, students, let us take one more example to clarify this concept. One is benzene. If I talk about benzene, benzene basically has two kinds of bond. One is carbon-carbon single bond, another one is carbon-carbon double bond. When I talk about these two bonds, I know that carbon-carbon single bond is longer as compared to carbon-carbon double bond, which is shorter. So the bond length of carbon-carbon single bond comes out to be 1.54 Armstrong. And when I talk about carbon-carbon double bond, it comes out to be 1.34 Armstrong, which is shorter. So according to these, the experimental data, if I'm going to draw the structure of benzene, how would it look like? This is the, single bond. Okay. Then comes double bond, which is shorter in length. Then comes single bond, which is longer in length. Then comes double bond, which is shorter in length. Then comes single bond, which is longer in length. Then comes what? Double bond, which is shorter in length. So this is the exact structure which should look like this, but it does not look like this. How does it looks? It looks like this. Now, ma'am, what you have done? You said that, okay, according to the data, the single bonds should be the longer ones and the double bond should be the shorter ones. These are all carbons according to the bond line notation. You all understand this concept, right? These are longer one, while these are shorter one according to this data. But this is not the real molecule. The real molecule looks like this. This is again resonating or resonance hybrid. Now, what is this? The dotted ones. What are these dotted ones? These dotted ones identifies the delocalization of pi electrons in the conjugated system. And it also explains us that all bond lengths are equal due to the delocalization. Hence, this data fails and all the bond lengths are now equal in length. Now, what is the new definition that comes out of the resonance, students? I would say it is the delocalization of pi electrons in the conjugated system. Now, the new definition, the previous definition was that when single structure cannot explain the property of resonance, we require more structure. Now, the new definition that comes out to be is delocalization of pi electrons in the conjugated system. Now, students, question arises, okay, ma'am, we can understand delocalization refers to the movement. Pi electron refers to the double bond. But what do you mean by conjugated system? Conjugated system, students, here refers to presence of parallel p orbitals. Don't get worried, we are going to see in depth about conjugated system also. Okay, it refers to the parallel orbitals. Now, students, if I talk about conjugated system, basically conjugated system can be classified into two sub basic categories. One is when A is double bonded with B and is single bonded with C. Now, this C may contain a positive charge It may contain a negative charge. It may contain a lone pair of electrons. It may contain a double bond. It may contain a triple bond. It may contain a radical. This is the very first thing that can arise. Okay. Another conjugated system can be when A acquires a negative charge or a lone pair. It is bonded with B, and B here acquires positive charge or vacant orbital. Now students, basically these are two concepts that can be seen in the conjugated system. We will see all of these cases. We will see one case when there is positive charge over here, when there is negative charge, then we will see the case of lone pair, then double bond, triple bond, and then the case of lone pair. We will see all of these cases, but these are the conjugated system basically. Now if I talk about the conditions for resonance, what are the necessity conditions that due to which resonance can occur? The very first condition is molecule should be planar. Now students, if I talk here, molecule should be planar. Now, planarity, I will explain you what do you mean by planar and non-planar in aromaticity, very depth. But here we need to understand, to find out is it planar or not, just we need to check out if it is sp2 or sp hybridized. It is generally seen. Okay. Now the first condition is molecule should be planar. The second condition is conjugated systems should be there. Now I have already told you the conjugated system can be of two basic subcategories, but to classify it further, there are basically some of the cases that we observe over here. There are basically 5 cases that we are going to see. The very first case, students, very first case is going to see when there is A double bond B, single bond C. Now as I told you, C can have positive charge, negative charge, lone pair of electrons, radical, है ना? So here the very first case is when C is acquiring positive charge. In second case, students, A double bond B, C is acquiring either lone pair or electrons. Clear? Lone pair or electrons, I would say. The next case is A is double bond B and C is acquiring a radical. Radical refers to one electron, right? We have seen in the homolytic cleavage, right? When there is one electron, radical arises. Then comes a case when A is double bonded with B, then B is single bonded with C, and C is further doubly bonded with D. As I told you, C can acquire either positive charge, either a lone pair, either electrons, either a double bond, triple bond. So here is a case of double bond. And the last case is when A acquires positive charge or vacant orbital, or you can interchange also. A acquires a negative charge or lone pair and B acquires a positive charge or vacant orbital. Here is a bond between them, so you need to kindly mention the bond also. Now students, here what we need to see, we need to see the electron density within the molecules. Here what we are going to observe, we are going to observe all about electron density. Okay students, now let us see the very first case. What we will see, when will resonance take place. Here we are going to see when will resonance takes place. So this is the very first case, when does resonance occurs or when does resonance takes place. Now if I talk about the very first case, it is the case when A is double bonded with B and C acquires a positive charge or a vacant p orbital. Basically positive charge is also vacant p orbital. Now what do you observe here? They say draw the resonating structures. Now how to draw resonating structure? We will learn to use the arrows, in which direction we need to break the bond, in which direction the electrons movement are being observed, in which direction is electron density more. So we will observe this very basic concepts over here. Kindly listen to me very carefully. I'm going to draw the structure all over here again. It is CH2 double bond CH, single bond CH2 positive. Now students, see, you need to understand first of all what is the thing, that whosoever is having more electron density will give its electron to the one which is having less electron density. So here we know that this double bond basically contains electrons, and this positive charge is basically what? Vacant orbital. It is the one which is empty, which requires electron, while it already have electrons with it. So here movement will occur from more towards less. Now what will happen? See, this double bond will break over here. this double bond will break over here because it has electrons and it doesn't have. So it will break over here. When this will break over here, what do we observe? I am going to use this arrow. Now what is the use of this arrow? This arrow refers to as this is the first resonating structure, and the one which I'm going to make will become the next resonating structure. So this represents the resonating structures, right? Now what is happening? See, you have to write CH2 as it is. Okay, single bond is as it is with CH. Here also single bond is as it is with CH2. Now what happens? This double bond is shifted over this. Now this double bond contained 2 electrons. When 2 electrons, see what happens over here, electron moves from here. Double bond is broken, the electron move from here to this direction, and this acquires a double bond over here. Now when this acquires a double bond over here, this positive charge is neutralized. Now what are you speaking? We are not getting. See, positive refers when there is no electrons, but when you acquire a negative charge, you become neutral. How? If I say you have +2 charge, and if I give you -2 charge, will you become 0? Yes, because equal positive and equal negative should be there to become a molecule neutral. So if I say it has a positive charge, when it will acquire a negative charge, it will become neutral. Hence, this CH2 will now acquire no charge because it is now neutral. But what is going to happen over here? Very interesting fact that you need to keep in your mind. This CH2 basically loses its electron. When it loses its electron, when someone loses its electron, it itself acquires which charge? Positive charge. When you are gaining electrons, students, you are acquiring negative charge. But when you are losing electrons, you are acquiring positive charge. So which charge acquires over here? A positive charge is generated over here. Now this and this structure, both of these are resonating structures of each other. Now this arrow defines of the resonating structures that you are drawing. Now let us see this case. It is quite interesting. I am going to make it here all over again, a bit wider. See, this is my case, right? Okay, now first of all we need to see where is the conjugated system. What is the conjugated system? A double bond B single bond C. See, this is A, this is B, this is C. See, is it the same conjugated system? A double bond B single bond C, and C is acquiring positive charge. Yes ma'am, it is the same system. If you see the system, this is A, this is double bond B, this is single bond C, and it acquires a positive charge. Same system. See the comparison. This is a conjugated system. Now, if I talk about this conjugated system, you know that resonance occurs in the conjugated system. Delocalization occurs in the conjugated system. So here, how does delocalization occurs? We have seen that this is the area where we can observe conjugation. Kindly understand, it is very important. This is the area where we are going to observe conjugation. Now let us observe the conjugation. See, this double bond contains electrons. It will break in between the B and C. See, here what we did. Here these electrons were broken in this direction. And what we acquired, we made a structure where A got positive charge because the electrons were moved. And here is this. Basically, this was formed. So what happened? The bond between A and B was sent towards B and C. The bond between A and B is sent towards B and C. Right? Now, what is the structure? We will draw over here. Now, to make a resonating structure, we require this arrow. Yes. Now, see. Okay. If you see over here, now this double bond of electrons are shifted towards here. So, this will acquire a double bond over here. You can see the double bond over here. Now what is going to happen? See, this C is basically positive. It is getting some electrons over here between B and C. So it will become neutral. See here, it is becoming neutral because electrons are moving here. It became neutral. It became neutral. Similarly here it became neutral. This carbon became neutral. Now what happened? Now this bond is being broken. The electrons from A are moving in between B and C. Still B has electron, but A doesn't have electron. First electrons were in between A and B. Now the electrons are between B and C. So B basically still has electron, but A doesn't have. So A is now losing electrons. When A is losing electron, when one is losing electron, what charge does it acquire? It acquires a positive charge. Okay. Now, is this structure complete? No. We still missed out this bond. This bond is still present over here. Now, can we make one more resonating structure from here? Yes. How can we make? See, how can we make? Now, what is the conjugated system over here? This is our A, this is our B, and ma'am, this is our C. C. Now, what happened? We made first conjugated system over this direction. Now, it came in this direction. Now, again in this, now the new conjugated system is going to be this. See, when the new is going to be this is going to remain same. This situation is going to remain same. The next resonating structure will look like how? Let us see the next conjugated system. I'm going to draw it over here, okay? Okay. This is the same situation. This bond is constant now. This is not in the conjugation. This is not in the conjugation. So we have drawn it as the same. Now what happens over here? What happens over here? See, this double bond is broken between B and C. So B and C now acquires a double bond and A is losing electrons. So when someone is losing electrons, it requires a positive charge. So these are the three resonating structures that you have observed over here. You know, these are the three resonating structures. So it is quite interesting concept. Okay. Now let us apply over one more in this same case. In which case? In A double bond B single bond C, and which acquires a positive charge, right? Now students, to check over here, now what we need to do over here, it is simple, quite simple. If it is A, if it is B, if it is C, now what here it is going to happen? Let us see over here. The bond between A and B is going to break in between B and C. What we are getting? A single bond B double bond C, and it requires a positive charge. The bond between A and B is broken between B and C. The bond between A and B is broken between B and C. Are you getting my point? Now what happens over here? We are going to make a resonating structure. So this arrow comes. Now, see, double bond arises over here because now this bond is moved to this, but A will acquire with charge positive. Why? Because A is losing some electrons. When someone is losing electrons, it acquires a positive charge, right? Because it became empty. So it acquired a positive charge. Now, this C, this carbon, C is not carbon, C is basically the atom. Here we know that C is carbon in this case. So now this C is now neutral, right? Is this structure now complete? No. One more conjugated system you can observe. See, in the very first case, you observed the conjugated system in such a way. Now, if I talk about this system, what you are going to see? You are going to see in this way. How come? See, here what you are going to see, here you are going to see that this is your A, this is your B, and this is your C. So what you are going to observe over here, the bond between A and B is going to break between B and C, right? Now the next resonating structure which we observe over here is this. See, what happens? This bond comes now here, and A will acquire with charge, positive charge, because electrons are moved away from A, and this C becomes neutral because it is gaining electrons, right? So this is the next resonating structure over here. Now students, if I ask you, can you draw one more structure? If you're going to draw one more structure, you're going to observe the same structure. So here again you have seen the two resonating structures for that case. Basically these are three resonating structures. One is that, second and third. Clear? Now you are able to define the case one very easily. You are able to use the arrows, the movement of arrows from more towards the less, from where electrons are present and where electrons are not present, right? So this practice is required. Because when you are going to see an examination, you're going to get confused that how I'm going to draw. If you are not going to draw from the very basic, you can't move to the complex level. So start from the basic and move towards the complex level, right? Now this was the case one. Moving towards case two. What is case two? When you are observing A double bond B, single bond C, and C acquires either negative charge or lone pair. Now I'm going to take both of these cases. Now what are both of these cases? See, A double bond B, single bond C. Now C is either acquiring negative charge or acquiring a lone pair. Let us make both of these cases over here. See, the very first case, A double bond B, single bond C, negative charge. The next case is A double bond B, single bond C, and the lone pair. Or I would say directly we can draw lone pair over here like this. It is up to you. I'm just writing lone pair. Okay, now see what do you observe over here. Now, as I told you, the movement of electrons will occur where electrons are present to where electrons are not present, right? So, what do you observe over here? If I talk about this case, see in this double bond, electrons are confined to the double bond. But if I talk about this negative charge is also basically two electrons. So, here it is not confined, it is open. So the open ones are more as compared to the confined ones. So the movement will occur from more towards the less. Now this doesn't have. Now this bond will be broken over here. See what I am doing. This negative charge is moving between B and C, and this bond between A and B is being broken. Why? You will observe that, ma'am, why there is a need to break the bond between A and B? Please keep no. Then it will, finish the valency concept. We need to maintain valency also, no? For that situation, we break the other bond. This is what conjugation is. When you are observing such cases, in the very first case, what we observe, the positive charge is present with the carbons that have the double bond. Now here we see the negative and the lone pair. So this is a conjugated system. Now what happens over here? What kind of resonating structure you can draw from here? Now, first of all, make single bonds. Single bond B, single bond C. Now, this negative charge, that means two electrons are moved here, acquires a double bond. Now, what happens? This double bond electrons are moved to A. Now, when someone gets electron, which kind of charge that species develop? Negative. When someone loses electron, which kind of charge does it develops? Positive charge. Now, electrons are coming towards A, so it will acquire negative charge. It will acquire negative charge. Clear? Hopefully this concept is clear to you. Now we are getting this C as a neutral, है ना? Now what? See, in this case, if I talk about, again, there is electrons in this double bond and there is electrons in this lone pair. Now if I talk about double bond electrons, they are confined to a particular region. But when I talk about lone pair electrons, they are not confined to a particular region, they are open up. So the electrons movement will occur from lone pair towards here, and this bond will break over here. Now what happens? Let us see. A, single bond B, single bond C. Now this lone pair is coming, so there is a double bond between B and C. Now what happens? See, there is a quite different thing. Here this bond is breaking over here, so it will acquire negative charge because A is getting electrons. When someone is getting electrons, it acquires a negative charge. But the new thing that we see here, see, basically when there were lone pairs, we say that the species was neutral. We don't consider the species to be negatively charged. Lone pair is also two electrons, but we don't consider it to be negatively charged. We consider it to be neutral. But when something from neutral goes out, especially electrons, so the neutral will get which charge? Positive charge. So here C will acquire positive charge. So you can understand the basic difference. In this case, when there is a negative charge, negative goes, so you become neutral. But when you are already neutral and electron goes, so what are you? You are positive because electrons are moving far from you. So here there is a charge development on C, but here there is no charge development of C. So this is a kind of different concept that you observe over here. Now if we see these cases, see, if I talk about this very first case, what is happening over here? Kindly consider any one of the system. I am taking this one of the system. Okay, now let us see the movement. See, this negative is open while this double bond is confined. So this negative will move in this way and this double bond will break over here. Same situation. See, A double bond B, single bond C, and C acquires a negative charge. Now what is the resonating structure that we are going to observe over here? See, this is the carbon, single bond oxygen, single bond oxygen. Now here this electrons are coming in between the carbon and oxygen, making a double bond, while this double bond is broken to the oxygen. Now oxygen acquires which charge? It is getting electrons, so it will acquire negative charge. Okay, now this oxygen is already negative and negative is moving from it, so it becomes neutral. It became neutral. It lie in this category, right? Now this remains as it is. This remains as it is over here. Now does anything else arises over here? Yes, ma'am. One more conjugated system we can observe. This is the another conjugated system that we can observe over here. Now how come another conjugated system? Let us see. See, if I talk about this case, again this is A, double bond B, single bond C, and negative. Now this negative charge will move over here and this double bond will break over here. Clear? Now what is the resonating structure we are going to draw over here? This is the carbon atom, this is the oxygen single bond, this is the oxygen single bond, right? Let us make this first because it remains constant. It remains as it is. This is remaining as it is. Now what is the difference we are seeing? This double bond is moved to oxygen. It acquires a negative charge. Now this negative charge is coming in between these. So it requires a double bond. So these are the resonating structures which we are observing. Now let us make one more resonating structures. If you say, ma'am, let us make this as a conjugated, you are going to get the same structure. So these are the resonating structures for this case. Clear? Now let us take this case where lone pair of electrons are present. This was the case when negative charge was present. So the C became neutral. So this became neutral. You know, this became neutral. This became neutral. But now in the lone pair case, C also acquires a positive charge. So don't get confused. It is quite interesting and quite confusing. Students, you know, they get confused in both of these and they do the questions wrong. But when you are getting the concept very easily, kindly make a differentiate table in both of these and draw the structures. While you'll practice, you'll get the concept more. Okay, now see this second part here. It has lone pair of electron. Now only one lone pair of electron will participate in the conjugation. So what happens? This lone pair of electron will move here and this double bond will break over here. Now again see over here, this is our this is what? This is our A, this is our B, and this is our oxygen is our C, which has a lone pair. A double bond B and C is having lone pair. So this is the case. This is the case. C lone pair will move in this direction between B and C, and A and B double bond will be broken over A. Now what is the first resonating structure that we draw from this? First of all, we are going to make like this. I'm going to write OH. Now, the upper one lone pairs are as it is. They are not involved in the delocalization. So, I've drawn it as it is. Now, what happens? This is also as it is. It is not involved in the conjugation. The part that is involved in the conjugation is this one. Is this one, right? Now, what happens over here? Kindly see. Double bond arises in between this due to the lone pair. Now this double bond is broken to this A, which acquires which charge? Which acquires a negative charge. Which acquires a negative charge, students. Now students, let us see the next conjugated system over here. So students, look over here. Now what happens? Now this A acquires negative charge. Now which concept you are going to use over here? Now see this. It is a quite interesting concept. Why? Because this is now case 1. Now this is case 1. First it was case 2 because it had lone pair. Now students, what happened? It have a negative charge. But still it is incomplete. Why? Why it is incomplete? Do not forget to mention that now C acquires a positive charge. When lone pairs are gone, that means from neutral, electrons are gone. So it requires a positive. So here positive will also come. Do not forget this. Otherwise your whole structure is wrong. Now here, this is the case 1. This is now this case. Simple. Now what happens over here? This negative charge will move over here and this double bond will move over here. So what we are going to get, our next resonating structure will be like this. This OH is as it is, positive, and here is a lone pair of electron. Here is a double bond. The new thing that we observe over here is a double bond arising over here and a negative charge over here. So you can check it out. This is the next resonating structure that we have made, right? So it is quite interesting, right? Now let us see the next case. That is case number 3. Now what is case number 3? When A is double bonded with B and C has a radical on it. Now let us see first what I'm going to tell you. A is double bonded with C and A is double bonded with B and C has a radical over it. Now what happens over here? See, a radical is basically 1 electron, while lone pair is basically 2 electrons. So what happens over here? This, this is broken over here. That means this 1 electron comes over here. Now to make a bond, we require 2 electrons. 1 electron is coming from C. Another electron will come from this side. This has 2 electrons, right? Now this 1 electron is moving in this direction, while this one will break here. Now as I've already told you in the bond breaking, that this means 1 electron. And this arrow refers to as 2 electrons. So you have seen whenever we were making these kinds of arrows, these were the movement of 2 electrons. Now we have used this arrow. This is the movement of 1 electron. Clear? This radical, red one, is coming over here and 1 electron from here is coming over here. Now one bond has 2 electrons, so one is moving here and another is moving over A. So what we acquire over here, what does the structure is being made over here? A acquires 1 electron, so it has 1 radical now, and then single bond is left between A and B, and now there was a single bond between B and C, but one more bond is made over here. How is this one bond made over here? One electron from the B and another electron from the C made a double bond. So this is the resonating structure that we observe over here. Now see the cases. If I see the cases here, kindly correct it here, radical will come. Let me make this structure a bit big for you. CH2 double bond CH, single bond CH2, which has a radical over here. Now how to make a resonating structure for the students? What we are going to do, we are going to break this radical over here, and this it has 2 electrons, so one radical over here and another radical over this. So what we are going to get? Another. See, again, for resonating structures we are using this arrow. Now what comes? CH2 acquires a radical while there is a single bond between CH. Now here double bond CH2 will come. So this is the resonating structure for this. Now let us see this case. Now students, if I talk about this case, now in the second case, again we are going to see the radical one, right? So this is going to be the conjugated system over here. Now see. If you are getting confused on how to draw, kindly mention A, B, C. So it will be easy for you to understand. See, if I'm going to mention over here, this is A, this is B, and this is C, which is having a radical. So now it is easy for me. Now I have to break the bond between A and B into two parts in the radical. See, here this is broken over here, this electron is broken over here, and this radical is broken over here. Now this double bond is here double bond is going to become. So how it will look like? See, here becomes a double bond, here becomes a double bond, while here the electron comes over A here. Are you getting my point? Is it easy for you to understand? So this is the resonating structure that we can draw. Now you say, ma'am, now make it again. You will get the same product. So when you are getting the same product, that means this is only the last resonating structure that you can obtain over here. Now students, comes the case 4. Now what is case 4? It is quite interesting. Now this case 4 is when A double bond B, single bond C, double bond D is observed. Now how to make this structure? It is quite simple. Either break the bonds in this direction. Okay, when you are breaking the bonds in this direction, so what you are obtaining? First of all, make the single bond, because you are, showing the movement of double bond only. So this double bond is broken over D, so it gets electron, it will acquire negative charge. This double bond is broken into B and C, so it acquires a double bond. While the electrons from A are being moved, so it will acquire which charge? It will acquire positive charge. So this is the structure. Now if you say, ma'am, kindly break in this direction. A double bond B, single bond C, double bond D. We have this case. Now if I break in this direction, so what I'm going to get? A, single bond B, kindly correct this. It is like this. Okay. Double bond C, D. Now D is giving its electrons, so it will acquire positive charge because something is moving away from it. And A is gaining electrons, so it will acquire negative charge. Now you will say, ma'am, how to identify in which direction the bonds are being broken? How to identify this? To identify this, students, we see the electronegative concept, which is more electronegative, which is less electronegative. But in general, you are going to get the simple cases only like this. Let us see this case first. If we are seeing this case, it is like this. Okay, now kindly listen to me very carefully. If you are getting confused, again I'm telling, this is your A, this is your B, this is your C, this is your D. Either go in this direction or go in this direction. Okay, but you have to go in one direction. Don't go one in between the direction. That is not the right concept. So if you are moving in this direction, what happens? This double bond is broken over here and this double bond is broken on D. Like this. Like this. So what is the resonating structure that we obtain from here? The resonating structure that we obtain is like this. The double bond is shifted between B and C, right? Now this double bond is shifted to D. Now this, if it is gone to D, that means D is acquiring electrons. When D is acquiring electrons, D is getting negative charge. So here is a negative charge. Now this A is losing electrons. When someone is losing electrons, it is getting positive charge. So this is the resonating structure that is being drawn from this, right? Now students, if I draw from this, kindly see this structure. Here, this is your A, this is your B, this is your C, and this oxygen is your D. This oxygen is what? It is your D. Now what happens over here? What happens over here? See, this double bond is broken over here. Now this is broken over here, right? Now see, what you are going to get. It is like this. Now double bond is broken to oxygen. So oxygen acquires electrons of the double bond. So it acquires a negative charge, right? Now this double bond is breaking between B and C and getting a bond here. A is giving its electrons. So it will acquire a positive charge. So this is the resonating structure that we can obtain over this. Okay. Now students, moving to the next case, that is your case number 5. See what it is given to you. Lone pair and vacant orbitals are present on adjacent atom. Whenever you are getting lone pair and vacant orbitals, okay, are present on adjacent. Now see, here, this is lone pair, this is positively charged. Positively charged is basically the vacant ones. This is the vacant ones. Now, as I told you, the one which is having electrons will give its electrons to the ones which is not having electrons. So, the movement which we observe over here is from this lone pair which is having electrons towards which is not having electrons. Okay. Now, what is the structure we are obtaining from here? The resonating structure, CH3 is as it is. Single bond NH is as it is. Single bond NH2 is also as it is. But this lone pair is moving its electrons over here, making a double bond. And this CH2, which already had a positive charge, now gets what? Now gets some electrons, so the charge is neutralized. When the charge is neutralized, no charge will come. But this NH is losing its electrons. This NH is basically losing its electrons. So this NH will acquire which charge? Positive charge. Are you getting my point? Now students, let us see this one. In this case also it is quite simple. But yes, kindly put star over here. It is quite different also. What you will observe, see. First of all, we are seeing this case only. But see what is going to happen over here. Now this pi bond, you see this system. One is this system. One you are getting this system. Now, if you see this system, what do we observe over here? What do we observe over here? That this double bond, let me make it from another color. This double bond contains electrons, so it will move towards this case. This case we have already studied. When there is a double bond B and C acquires a positive charge, you can see the case 1 or 2 it may be, right? Now, what will be the resonating structure over here? See, here this double bond is broken over here like this, and this positive is now neutralized because it is getting electron, but this one is losing its electron. This one is losing its electron. So it will get which charge? It will get which charge? Positive, because it is losing its electrons. Now acquires this case. Now comes this case when oxygen basically has lone pair of electrons. So it will break in this direction. It will break in this direction. This was the case 1. This is the case 5. Now this conjugation basically is the case 5. Now see what happens over here. Now the next structure. Now the lone pair comes over here. The lone pair comes over here. Now this oxygen loses its electron. So it will acquire which charge? Positive charge. It will acquire positive. And hence this is as it is. This is as it is. Clear? So this is the resonating structure. It is quite a different case because here 2 cases are being involved. Now students, other than this, there is also a special case when negatively charged is directly attached with atom containing vacant d orbital. I am repeating again, when negatively charged is directly attached with atom containing vacant d orbital. So this is your special case, or case number 6 you can say. Now students, what happened in this case? Let us take one example, that is CH2 negative and is Cl. Okay. Now see. What we see over here, when negatively charged is directly attached to the one that is vacant. So what happens over here? This negatively will move in this direction. So what we are going to get? We are going to get CH2 Now double bond will arise over here. Now when CH2 basically loses its electron, it will become neutral because it already had negative charge. But when this Cl will gain some electrons, so it will acquire which charge? Negative charge. It will acquire which charge? Negative charge. So this was the special case, students. So hopefully you have understood all of these cases. Now comes the most interesting part, that is draw the structures. Which structures? Resonating ones you have already learnt from me in these 5 cases and one special case. But here you have to also draw resonating hybrid. So it will be quite interesting for you. I want you all to stop the video first, write the question first, make the structure first and match with me. So it will be quite interesting, and we will also calculate that how many of the questions you have done correct, right? Okay. Now students, this is your first question. Let us see how to draw the structure. Now we will apply all the cases all together. First we will make the resonating structures, then learn the resonating hybrid also. Do not skip the video like you know the answer. You know only resonating structures. We will understand resonance hybrid also. So see here in this situation, I'm going to draw this a bit big here. This is our structure, right? Okay. Now what happens? This is our first conjugated system. This is our first conjugated system. So what happens over here? Double bond is broken over here. Now you know this thing, A double bond C, B single bond C, which is having a positive charge. Now what is the resonating structure that is being made from this? C. When this is constant, this remains as it is. Okay. Now this double bond is being broken here between B and C like this. And when C acquires some electrons, which is already positive, acquires some electrons, becomes neutral. Quite easy. But this A loses electrons. So this will acquire which charge? Positive charge. This will acquire which charge? Positive charge. Now comes one more conjugated system. Which one? This one. Again the same concept, A double bond B, single bond C, positive charge. Now here what will happen? See, here this double bond will be broken over here like this. What is the resonating structure that you are going to observe? This remains as it is. Now this double bond is broken between B and C. Okay, this C already had a positive charge. When electrons came over here, it became neutral. Yes. Now this atom A loses electrons, so will acquire which charge? Positive charge. Now any more resonating structure can be made? No. So these are the resonating structures. Which one? These are the resonating structures. This is the resonating structure. This is the resonating structure. This is the resonating structure. While this is also a resonating structure. Now let us make a resonating hybrid. Now what was resonating hybrid and what were resonating structures? Let us revise once again. In resonance, what I told you resonance, what we observe when a single structure cannot explain all the properties, we require resonating structure. So now this single structure couldn't explain all the the properties, so we made these structures which explain the property. Now which structure? There is a real structure. Now let us make that real structure, which is resonance hybrid. Now this arrow was used to represent a resonating structure, and this is used to represent a resonating hybrid. How to make a resonating hybrid? First of all, make these bonds like this. Now when there is a delocalization of pi electrons, from where? See, first pi electrons were present in between here, so make a dotted line. Then you can see the pi electrons came here in between these. Yes. Yes. Then you see this, there was also pi electrons present over here. Yes. Then you see that pi electrons came here, right. So this is the resonating hybrid, where we represent all the double bond, where the double bond were made. Here double bond was present, here it was present, here it was present, here it was present. So we made it with the dash. Right? Now we need to represent charges also. See, now we can't directly write positive charge or negative charge. We will write partial charges because we see different structures and the charges are present on the different positions. So partial charges will come. First it was present over here, so here it is partial positive. The next time it was present over here, so partial positive. The next time it was present over here, so partial positive. So this is what? This is a resonance hybrid. This is a resonance hybrid. Clear, students? Okay. Now let us see the next case, students. If I see this case, draw the structures, resonating structures as well as resonance hybrid. If I talk about this structure, again what we need to see? First, this is going to be the conjugated system. When there is A double bond B single bond CN positive, so what is going to be happening here? Here, this double bond is going to break over here. So what we are going to observe? We are basically getting, see, this is as it is. This double bond is now broken over here like this. Now, this C, which already has a positive charge, when gains electron becomes neutral, while this A is losing electrons, so it will get which charge? Positive charge. Clear? Now, the next conjugated system, which one will be the next conjugated system? Now, this will be the next conjugated system. How come? How come this is going to be the next conjugated system? This double bond will be broken over here. Now, when this double bond is being broken over here, see, this is as it is. This is broken over here. This become neutrals because it is getting electrons. And this, as it is losing electrons, will gain a positive charge. It will gain a positive charge. Okay. In the next case, if you are going to observe, students, what is going to happen? If you are going to break it again like this, in this conjugated system. This is going to be the next conjugated system, where which we are observing here, the double bond is being broken over here. This double bond remains as it is. This double bond came over here. It is neutralized. It is losing electrons. Clear? Now, if you are going to repeat this, you are going to get the same structure. So, these are the resonating structures. What is the resonance hybrid over here? This is the representation of resonance hybrid. Now, to make a resonance hybrid, we need to see the double bonds. Where are the double bonds present? First, it was present over here. Second, it was present over here. Okay. Then it was also present over here. Okay. Was it present over here? Yes, in this one. Was present over here? Yes, in this one. So this is the resonating hybrid. Now to mention the charges also, see. Here there was charge, so we will write partial positive. Here there was charge, we will write partial positive. Here there was charge, we will write partial positive. Okay. Where else there was charge? Let us see. There was a charge over here also. So we will acquire a partial positive charge over here also, students. And one charge is over here also. So this is what a partial positive charge. Clear, students? If I am going to see this structure again, see, when you are moving from this direction, partial positive is coming over here. When you are moving in this direction, partial positive is coming over here. What you are going to do next? When you are moving in this direction, students, one second, let me tell you. Here, what is going to happen? This structure will not come first. This is not going to be the conjugated system. Sorry for this inconvenience. Kindly see this again. Because there is one missing. Because this was missing, that means there was one more resonating structure. So this is the identification. While mentioning the charges, kindly check that you should obtain these much structures only. So what I'm getting over here, it was like this. This double bond came over here. Here we got positive charge and here we got this. Now what is happening over here? See, now what happens? This double bond is broken over here. Okay. When this double bond is broken over here, what we are going to get? We are going to get one bond over here, the positive over here and this positive over here. It became the same molecule. Okay. And if I broke this in such a situation, let us see one more case. If I broke this here, then this double bond came over here, positive came over here, and this came over here. This structure, I went in this direction. If I go in this direction, which I already made me this structure. Now the structures which are similar, kindly cancel it out. See, any of the structure is similar? Let us check. Okay, these are not similar structures. Okay, yes, but this structure and this structure is similar. So you should cancel it out. Only one resonating structure is simple. So we are getting basically over here 3 structures. Other than this, let us check out if any else structure is observed over here. So if I see, students, this bond is broken over here. When this bond is broken over here, Okay, what we are getting, we will get a positive charge over here. This remains as it is and double bond is over here. Now you can see the positive charge is raised over here. How I identified that one structure is missing is with the help of charges, is with the help of resonating hybrid. So whenever you are doing questions, what do you observe? Sometimes you're making the same structures and you didn't even realize also. To make sure that it is correct, kindly make a resonance hybrid. And while making a resonance hybrid, kindly find out the charges. If the charges that you are making is somewhere absent, this is a technique to check out the question. Like I saw there was one charge missing, so I thought that yes, one structure is also missing, so I made two structures to find out the reality which one is correct, right? So it is like this, na? It came from this direction, so it is like this. So I got confused, that's why I made it again and clarified you all that these structures are identical, so I cancelled it out and this went into this direction. These are the 5 structures that can be obtained for this resonance hybrid. Clear, students? Now we will see our next structure. So students, now seeing the next case, we have this structure with us. First of all, kindly see what is going to happen over here. We have A double bond B and C is having positive charge, right? Now we know that this double bond is going to break over here. What we are going to get? We are going to get this structure. There is a double bond over here and there is NH3, right? And this positive will get neutralized while their double bond is being broken. So here it will be electron deficient, so gaining positive charge. Is this correct? Kindly observe it. Here nitrogen bonds are more, so it is not correct. It is not correct. No resonance will occur over here. Or I would say there is no resonating structures over here. Why there is no resonating structures? Because we need to keep in our mind the bonds of nitrogen as well, which are exceeding. So this is not correct, right? Okay. Now students, moving to the next structure. See this next structure. It is also the same conjugated system, right? This one, A double bond B and C is gaining a positive charge. Now, see, this double bond is being broken over here, right? What we will get from this? Right? See, this is as it is, this is as it is, and this bond is coming over here, right? While this carbon atom is losing its electron, so it is electron deficient, will acquire a positive charge. Now what will be the next conjugated system over here? Over here, students, this is going to be the next conjugated system. So when it is going to be the next conjugated system, I would say this double bond will break over here. Now when this will break over here, what we are going to get? What we are going to get? See, this is as it is, this is as it is. This double bond comes over here. Now this carbon is losing its electron, so will acquire a positive charge. Now, is there any another conjugated system? Many students will do this wrong. They will say this, no, but see, if it is A, it is B. This is going to be C. C is not having anything. To be conjugated system, this should have a double bond and then C should have a positive charge. But here C is having nothing. In fact, D is having a positive charge. So here no more conjugated system, no more resonating structure. Now to make a resonance hybrid of this, see, where does this bond movement was there or not? No. So this will remain as it is. Okay. Now what do we observe over here? We observe that there was this bond present initially. Initially this bond was present. Then what happened? What happened? This bond broke over here. This bond came over here. Okay. After that, what happened, students? This bond was also present, which broke over here, which broke over here. So this is the resonating structure. You can see this is the resonating structure. Here, here, There is no, double bond, partial double bond character over here, only in this direction, only where the double bonds are being observed. Now let us see the charges over here. First charge was here, so it is partial positive. The next charge came over here, so this is partial positive, and one charge was present over here, so this is partial positive. And hence, see, 1, 2, 3 partial positives, and we are getting 3 resonating structures, right? So it is checked also. So hopefully this was very interesting case. Now let us see the next case. In this case, I want you all to do this. Till then, I'll drink a glass of water. Excuse me. Kindly do this. Okay, students. Now coming back to the question, let us see this question. In this question, we have a lone pair. Now see, when there was A double bond B and C had a lone pair, now which category, from which directions the movement was seen? Lone pair was there when it was, it was seen, electrons were seen. By this, the electrons were confined to a particular position in the double bond. So the movement will be seen in this direction and this will be broken over here, right? Now let us see its resonating structures. Okay, now this remains as it is, students. Now the very next thing what came in our mind is this double bond is broken over here, so it gains electrons, gains a negative charge, while here there was a single bond between oxygen and hydrogen. Okay, and these lone pair came over here making a double bond. Making a double bond, students, kindly see this. But after making a double bond, see, whenever we have seen, whenever there is a lone pair, we consider what? It as a neutral. And when it is, giving its electrons, so it acquires which charge? Positive charge. So here positive charge will come. Clear? You know, when there were two cases, when they were negative charge and when they were lone pair cases, this was the lone pair case, right? Now, which will be the next conjugated system? Let us see. This is going to be the next conjugated system. Okay, now let us see the movement here. This again, there is a negative charge and there is a double bond where movement will occur from negative charge because it is open and double bond electrons are confined. So here this will break over here and this will break over here. Clear? Now let us make the structure. See, if you listen each and every step very carefully, then you can't do any mistake. But if you haven't listened any concept very clearly, then what you'll do, you'll break in this direction and it will went wrong. So you should know from which direction to which direction the bond should break. So these will be done only by practice. Okay, so here what we are going to get, see, the things which are kept constant is OH positive. This remains as it is, this bond remains as it is. Now see, this negative charge comes over here making a double bond and this double bond is broken over this carbon. So this acquires a negative charge. Why? Because double bond is breaking to a carbon. So when a carbon acquires an electron, so the carbon becomes negatively charged. So here negative charge come. Now what will be the next conjugated system? This is going to be the next conjugated system. And now for this conjugated system, students, see what will be the step. This negative bond will be broken over here and this double bond will be broken over here. Clear? Now what will be the resonating structure that we are going to get over here? Double bond OH positive is remained as it is. This bond is remain as it is. This negative charge comes over here now. Okay, this negative charge comes over here making a double bond, while this double bond is broken over here bringing all the electrons to this carbon. So when someone gains electron, it becomes negatively charged, right? Now let us see the next case. Now what is the next conjugated system over here? This one. How come? Let us see. Let us see, students, here. Again, this negatively charged will be broken over here and this double bond will be broken to the oxygen atom. Clear? Now let us see the structure. See, this bond remains as it is, this bond remains as it is, right? Now what happens? This negative charge makes a bond over here and this now double bond breaks over the OH. Now, when this double bond takes its electron, OH is already a positively charged. When positively charged gets a negative, it becomes neutral. So it became neutral and OH came. Now you will say, ma'am, this structure cannot exist because it is similar to this. No, it is not similar to this. Why it is not similar to this? See, very interesting fact. Here you can see double bonds over here. here and here. Now see here, here double bond arises over here, here and here. In that situation, now let me draw the resonating hybrid, you will get my concept. See, if I draw a resonating hybrid over here, how will it look like? It is basically like this, no? If I'm going to draw a resonating hybrid, see, initially the double bond were present over here, and over here. After that, the double bond came over which direction? If you see, the double bond came over here, here. Okay. Then the double bond came over which direction? If we see this structure, double bond came over here, this one. Okay. Now, if I see this structure, double bond came over here, this one. So you see, this and this can basically look like this. As I told you in benzene, we draw a circle. That means you can see the alternative position of the double bonds. In this case, double bond is present over here, here and here, while in this case it is present over here, here and here. Clear? Now this is the resonating hybrid. Let us make the charges over here. We see that OH, it acquires a positive charge. So here only this is getting a positive charge, not anyone else. So here positive charge will come. Okay. Now if I talk about negative charge, now negative charge are present at various positions. So partial negative will come. Where? See here, partial negative, then at this position partial negative, and at that position partial negative. So you can observe here carefully. See, there is one structure for OH positive, there is one structure only for OH positive if you see, and the partial negative ones, basically there are three structures. This is for partial negative, this is for partial negative, this is for partial negative. This is basically made when there is a separation of charges. If you'll see ma'am, there are basically 1 2 3 4 structures, and here there are also 4 charges. Here there are also 4 charges. One is for OH positive, another is for these 3. So it tells us where does the positive charges lie. But let me tell you students, it is still incomplete. It is still incomplete. While observing, you are making in such a way, but this is not the accurate way. How? See, if you know in the previous case what I did. In the previous case, what I did, first of all, I made the single bonds. Then I just made the bonds where the double bond was being seen. See, first of all, the double bond was seen over here, over here. Okay. The next case, where were double bonds? See, over here. Only make the arrow ones. Only make the arrow ones once. Okay. Then where does the double bond was seen? Over here. Here also is arrow. Okay. In the next case, where were double bonds seen? Over here. Over, you can see over here. Okay. And in this case also, you can see the double bond over here. Right? So here, students, you also see a double bond over here, which you didn't mention. So this was left that you need to mention over here. This becomes positive charge, while this you can directly write partial negative. It can also be expressed in such a way. Okay. Now students, both the structures are correct, but the correct was the one that I made afterwards. In this structure, students, in this I directly wrote partial negative. I didn't mention it individually, and this also you need to mention because the double bond came over here also, right? Okay. Now seeing to the next structure, here in this structure is again the case where we have negative charge, we have double bond, so the first conjugated system will arise over here only. Now how? Let us see. This negative will break over here and this double bond will break over here. So what will be the conjugated system that we are getting from this? This remains as it is. We are getting electrons over here because this double bond breaks over here and this negative electron moves over here, making a double bond, right? So this is the very first structure that we are obtaining from this direction. Now the next conjugated system is this one. Okay. Now let us see this. If we see this, negative one is the open ones and the double bond ones are the confined ones. So this will break over here and this will break over here. So what will be the next structure that we are going to get? So in the next structure, see, this negative is coming over here, right? And this double bond is breaking over the oxygen, making it a negatively charged because it contains electrons that are breaking on the oxygen atom. So this is the resonating structure that we observe in this structure, right? Okay, moving forward to the next case of the radical one. It is very interesting, okay? And you know how it is interesting. First of all, we need to identify where is the conjugated system. So see, here is the conjugated system. Now what we need to do is, see, Again, I'm telling you, if you're being confused, write A, B, C. It will be easy for you. Now see, this free radical will come over here. Now this radical will come over here of this double bond, and this will break over A. Now what does it looks like? See, these remains as it is, students. Now this A gets an electron, so it, because this electron, this double bond is done as a homolytic cleavage, so the radicals will be formed. A will get one radical, and now this radical of B combines with the radical of C, making a double bond over here, and here CH2 arises. And here CH2 arises. Now in the next case, what will be the next conjugated system? Now this will be our next conjugated system. Again, I'm going to write ABC for you to understand easily. This is our A, this is our B, this is our C with the radical. Now what is the next situation? In this, again, this radical comes over here. Now this doubly bonded radical, one electron comes over here and other electron goes to the A, right? Now what will be the structure that we are going to obtain from this? See, this double bonds remains as it is. This double bond CH2 remains as it is. Now what happens over here? This radical and this radical combines, making a double bond over here. And this now double bond gets a radical on A. This gets a radical on A. Clear? Now, we are getting another conjugated system over here. This one. Now, in this again, we are going to write it is A, it is B, it is C with the radical. See, if you'll write this, you'll not get confused. So now this radical is coming over here. This doubly bonded, one electron comes over here, one electron goes over here. One radical refers to one electron. Now the next structure is going to be, see here, what happens? This remains as it is, while this remains as it is. Here the radical will come because the electron comes over A. Now here making a double bond like this. Here making a double bond. 1 second, students. Sorry, I made this double bond. It was like this, right? Clear? Now there is also one situation that arises over here. This one. Again, this is what? This is A, this is B, and this is C with the radical. What happens over here? Check it, check this. This electron comes over here, this electrons of the double bond come over here, and the radical goes to A. Now what is the structure that is being observed over here? This remains as it is. Now here double bond arises due to one radical from here, one radical from here. That means two electrons making a double bond. And this now single bond was already there and the double bond broke into radicals, right? And bringing one radical to this CH2. So this is what is the resonating structure for this, students. Now you can easily make for the free radical cases also, right? Now students, this ends our resonance portion. Now we know what is resonance. Now comes the topic that we were studying. We were basically studying the effects, right? One of the effects we have already understood is the inductive effect. Now comes our next effect, that is resonance effect or mesomeric effect. We have understood what is resonance in order to understand the mesomeric effect. Now, what is mesomeric effect? First of all, let me make a structure that we have done in resonance. See, you have been familiar from this structure which we have done already. This one. This structure we have made again and again, or I would say, let us make it a short. Why to make it a big structure? Okay. For example, if you have this structure, I want you to make resonating structures for this. Now you can easily make, yes, it is easy for you. Now what you will do? Either move in this direction or you can move in another direction. See, if I move in this direction, what I'm getting? I am getting a negative charge over here, a double bond over here, and a positive charge over here. But I can also make this in other terms. In which terms? See, let me draw this structure again. This was like this. But if I move in this direction, I can also go in this direction as well. So what is the resonating structure I am obtaining when I'm moving in this direction? Again, there is a double bond over here. Again, 1 second. Again, there is a double bond over here, a negative charge over here, and a positive charge over here. So there are basically two possibilities which I can obtain from this same structure. That means it is bidirectional. It is not unidirectional. Bidirectional means we can go in any of the directions. So to make it unidirectional, we require mesomeric effect. To make it unidirectional, we require mesomeric effect, students. Now, what do you mean by mesomeric effect? Mesomeric effect is the one which is like whenever I am adding a group to any of the molecule to make it unidirectional. As I've seen, we have seen it is bidirectional. To make it unidirectional, I am adding a group or an atom to make it unidirectional, to make in only a one direction, so that we could understand, yes, it is moving in the right direction, yes, it is moving in the left direction due to that atom. That is mesomeric effect. Now what I'll do, if I add in the same structure, students, like this was my structure. So if I extend my this structure and I add OH group, first of all I'm adding C double bond OH, this group. I have added this group over here, and due to this group, now see, due to this group I want you all to make resonating structures. Now make a resonating structures. How would you make a resonating structures? You know that there will be breakage of bond. There will be breakage of bond. In which direction there will be breakage of bond? First of all, write this. This is a group of atom, due to which now resonance will occur in only one direction. Due to which resonance will occur in one direction, called mesomeric effect. Okay, now students, to make this structure, first of all, we need to understand the breakage of bond. How to understand the breakage of bond? See, first of all, what happens over here? We know that oxygen is more electronegative than carbon. So there will be a bond breakage over here. This will break over. Let us take another color. This double bond will break over here. This double bond will break over here. So what is the resonating structure I am obtaining in this direction? See, this remains as it is. Now, if it is losing electrons, it will acquire a positive charge, because this eventually is losing a double bond, and this gains a double bond, and here is oxygen which is losing its double bond is breaking over this oxygen, gaining a negative charge. So this is basically the structure which we are obtaining. Now again we have a conjugated system over here. This will break over here, this will break over here, making one more resonating structure. Now, when this bond will break over here, this will acquire positive charge. Now, what do you observe over here? Is there any need to think whether to break bond in that direction or in this direction? No. You already know that, yes, in this direction only bonds are breaking, because oxygen is more electronegative. So, in this direction only it is breaking. See, in this direction only it is breaking, students. It is quite easy for you to understand that now it is unidirectional. You no need to break the bond in the another directions. So this is what it is, a mesomeric effect, when due to the addition of any group or any group of atoms, due to which the resonance occurs in only one direction, it is mesomeric effect. Now comes the types of mesomeric effect. What do you understand by the types of mesomeric effect? I would say mesomeric effect is further classified into plus M and minus M, which can also be referred to as plus R or minus R. See, basically, all mesomeric, mesomeric effect can be resonance. All mesomeric structures can be resonating structures, but all, you can see that all resonating structures cannot be mesomeric structures. Why? Because to be a mesomeric structure, you need to require a particular group. So all mesomeric, they are a resonating structure, but all resonating, they are not compulsory that they can be a mesomeric ones. So now, as I told you, types of mesomeric is plus M and minus M. Now to understand this, first of all, I am taking a case of, a group of atom which is Z. Let us take a case. For example, here this is double bond, and here there is an atom Z present over here. This is an atom, a Z present over here. Why I am adding an atom? Because I told you in mesomeric effect we need an atom that with the help of which the resonance occurs in unidirectional. So this group of atom or an atom basically can have a lone pair or negative charge. When it have a lone pair or negative charge, it becomes plus M group. When it have a lone pair or a negative charge, it comes under the category of plus M group, right? Now, let us take one example. If I put NH2 over here, this one, which has a lone pair. So what will happen, students, in this direction? Now you know that lone pair are the open ones and the double bond is the confined one. So the movement will occur in this direction. Now you know this, that movement will occur in this direction. That means it made it unidirectional. It made it unidirectional. So the group that made it unidirectional is basically refers to as mesomeric group. Now other than this, which other groups? Another one is OH group. Okay. Other than this is NHR group, S negative, O negative. So these are the categories. Other than this, students, another case I would talk about of minus M group. This was all about plus M. If I talk about minus M group, now let us take of minus M. Again, I'm taking a group Z over here. Now this Z, that Z had a lone pair or a negative charge. This Z is basically a vacant orbital. It can be a vacant orbital, or if is not a vacant orbital, it can be the one which generate a vacant orbital. Now let us take a case of BH2. If I put BH2 over here. Now we know that it have a vacant orbital. This boron has a vacant orbital. So the movement will occur in which direction? In this direction. See, when there is electron and when there is no electron, the movement will move from more electron towards the less electrons. So it will move in this direction. Hence, a resonance will become unidirectional, right? Other than this, you can take the case of CH2 plus 2. Again, when there is a positive charge, that means it is a vacant. So the movement will occur in this direction from more towards the less, from where there are electrons to where there are not electrons. Now see, there is a positive charge. This is a case of what? This is a case of generation. Basically, we are going to see when there are vacant orbitals, it is okay. But when there are not vacant orbitals, then there will be a generation of vacant orbitals. So the case 3 will be generation of vacant orbitals. So students, these were basically the types of effect. Now let us take one case for the generation of vacant orbital where we are generating the vacant orbital, the case 3. If I take this case, when I'm taking this case, now what I'm observing over here, see, we know that movement will now occur in one direction, only in this direction, right? So here we are generating a vacant orbital. What are we doing? Oxygen is getting a negative charge because this double bond is broken over oxygen, right? And it gains electrons, and this double bond comes over here, while here it will come positive charge because it is losing electrons. So this is the case where there is a generation of vacant orbital, which is the case 3, which comes under the category of minus M group. Clear? So now you have understood about plus M and minus M. Now students, comes the important concept, that is factors affecting mesomeric effect. Now what are the factors that affect the mesomeric effect? Number first is the size, students. More the size, less will be the extent of overlapping. More the size, less is the overlapping. Less is the overlapping. Now how to explain this? Let us take one case. See, in mesomeric we are going to get one on another group, right, attached. So here if I take NH2 which have electrons over it, the next case I take of PH2, phosphorus, you know, instead of nitrogen now I am taking phosphorus, and the last one is when I am taking ASH2. Okay, now students, as you know, these are of nitrogen family. Okay, now I want you all to understand that how does size affect mesomeric effect. To understand this, if I would say, for example, these are present in such a situation. See, when I talk about, I'm just making this bond. See, when a double bond when double bond is the you know, with the help of p orbitals, we know that with the help of overlapping of p orbitals. So if I say here, if there is overlapping of carbon and nitrogen, so it is quite easy. But when I move you know, in the group, down the group, the size becomes more. So I would say, for example, when there is carbon, now there is phosphorus, its size is more while carbon size is less. So there is a less amount of extent of overlapping. But if I talk about AS over here, again it has a big orbitals, it has small orbitals, so here also overlapping is difficult. So when the size is small, the extent of overlapping is what? When size is small, overlapping is good. When size is more, overlapping is difficult. So extent of overlapping becomes difficult when you increase the size. Hence I would say this is stable, then comes this, because it has less size, that means here overlapping is more, overlapping is good, as you can see over here. Okay, now students, comes the next factor, that is electronegativity. Now how does electronegativity affect? Electronegativity, more the electronegativity, less the donation. More the electronegativity, less the donation. Okay, now again to understand this, I'm going to take one more concept for you. For example, here is NH2. Now I am taking the case in which it's of same period elements. Okay, let us take OH. And let us take fluorine over here. So we have these three cases. Now students, what happened here is, we know that fluorine is more electronegative than oxygen, and then is nitrogen. We know this in general concept, in general knowledge we have seen in the starting. For electronegativity, more the electronegativity, less the donation. If it will donate less, then it will be less, then it will have less mesomeric effect. So this will be our criteria. More the electronegativity, less will be the donation, right? Now comes the third factor that we need to remember is cross conjugation. Cross conjugation is basically when there is an attack from both sides. How come? Let me tell you. If you have this case, so you know over here what happens. Over here you know that these lone pair of electrons can move over here and this double bond is broken in this direction. But now if I change this, a bit, what I'm making now, kindly see this. If I am doing this here, nitrogen is, yes, it is present over here, but what I have done now, I have added one more group, C double bond O CH3 over here, and hydrogen is over present. Now what happens over here? Now this nitrogen has two tendencies. Either it can go in this direction, means in this direction, or it can move in this direction, making this bond. Now this nitrogen has two cases. Either it can move in this direction or it can move in this direction. But this NH2 only had this case because it had double bond in that case. Here it can have two conjugated system. So when there is a possibility of two conjugated system, there arises a cross conjugation. This is a case of cross conjugation. This is a case of linear conjugation. This is a case of what? Linear conjugation. So whenever you are getting cross conjugation or linear conjugation, this is the main factor that arises, which is responsible for mesomeric effect. So we observe that linear one will have more mesomeric effect than the cross conjugation one. Clear? Now students, come the order of plus M group. As we have seen the order of inductive effect, similarly we are going to look out to the order of plus M group. Now to check the order of plus M group, it is quite easy for you to understand. See now. This again is most important, third one. But when there is a comparison between mesomeric group and inductive effect, kindly consider fluorine, chlorine, bromine as inductive effect, minus I effect. It is more minus I. In fluorine, chlorine, bromine, minus I is more as compared to plus M. As compared to plus M, minus I is more. This is an exception case. This is you need to remember. Okay, other than this, you need to learn of all of these. I am going to repeat. O negative is more, having more plus M group. Then is NH2, then is NHR, then is NR2, then is OH, then is OR, then is pH, then is fluorine, chlorine, bromine, which I have written separately for you to understand. Again, if you see NH2, OH, fluorine, this we have already seen. This we have seen the example in factors affecting, right? Because fluorine is more electronegative, right? So donation is less. We have seen this case. So fluorine, chlorine, bromine, iodine, I have already told you students that it will have plus M group, but minus I is more. It will be more effective than plus M. Now students, if I talk about this one, here it is CH2 negative, then is OH negative, and then is NH2, NH negative, then is O negative. So this is the order that you need to keep in mind for the plus M group. Other than this comes the order for minus M group. Now for minus M groups, we have seen both of the cases, for plus M, for minus M, right? Now for minus M, I would say it is NO2, then is S double bond O OH, then is cyanide CN, then is C double bond O NH2. Then here is, it is also arrowed, it is carried forward. You can directly write it in a horizontal line. We have C double bond OH, then we have C double bond O CH3, then we have carboxylic acid, then we have C double bond O OR, then we have C double bond of NH2. Then last one is this one. This basically has vacant orbitals with it. Okay, now this is C positive, CH3 positive. This is BH2, which is having vacant orbitals. So this is the order of minus M group, which you will see in the questions. Now if you don't remember that, there is no problem, but do remember this one. This is quite important. Kindly put a star over here because this is quite important. What is quite important over here? Let us see. See, now when they will give you some questions, they will ask you either compare M and I group collectively, like compare inductive group also and mesomeric group also together. So what you will do, see, whenever you are observing plus M group is present over here, so it has three basic possibilities. One possibility is that both the groups will be present, plus M also, plus I also. Okay, one possibility is that plus M group is present but is more effective than minus I, and another one is when plus M group is present but is less effective than minus I. Okay, so this is the case for plus M, but for minus M what happens? Whenever there is minus M group, there will always be minus I group. So it is quite easy. So first of all, I'm going to tell you minus M group only. Whenever there is minus M group, there is minus I group. That means here electron density is less, and these are electron withdrawing group. Here electron density is less, and all of these groups are electron withdrawing group. So whenever you are observing minus M, that means minus I is going to be present there, right? Now if I talk about plus M, first case is plus M and plus I both are present. In which cases this occur? In O negative, in S negative, in CH2 negative, in NH2 negative. Here they increases the electron density because both are plus groups. So here electron density is increased, students. Here electron density is increased, due to which they are electron releasing group. They will release electron. They will release electron. Electron donate. I will say electron donating or electron releasing groups. Electron releasing groups. Now the category come in which plus M group is also present, minus I is present, but plus M is dominating minus I. When plus M is dominating minus I, that is OH, OR, ET refers to ether, then ET refers to ethyl group, then comes NH2. So here plus M is dominating minus I group. Now what happens over here, students? Electron density is increased. What happens here? Electron density is increased in plus M, because it is it is what happening here. Electron density is increasing, here electron density is decreasing, but plus M is more. That means here electron density is increasing overall, right? Here electron density is overall increasing because plus M dominates. Now students, come when plus M doesn't dominates minus I. When minus I dominates plus M, that is fluorine, chlorine, bromine, iodine, which I already told you to put a star over here because it is quite important. It is quite important. Clear, students? So this was the comparison between M and I effects, which we need to know. Now we are going to apply over here. We need to identify M and I effects. Which of the following will have M effect or I effect? We need to see. Now the very first case is NO2 is present over here. If you remember, I told you in minus M group, we started from NO2. So here if NO2 is present over here, then minus M is present over here. It is but obvious. I have already told you in minus M, if whenever NO2 is present, there will be minus M. And I told you in the previous case, that whenever there is minus M, minus I will always be present over here. So here with minus M arises minus I also. Both of these arises, and both of these, what they are going to do? They are going to decrease the electron density. The electron density decreases. They are going to decrease the electron density. Now if I talk about this case, you know that O negative basically shows what effect? This electron will move here, this will move over here, right? So what will it do? It will increase the electron density over this carbon atom. So that means here plus M group is also present and plus I group is also present, because electron density is increased over what? Carbon atom. So if you remember the order, or if you remember which lies in which group, then you can easily identify the groups, right? Okay, now students, comes the next case in which NH3 positive. Again this case, why I have again put, because you are going to do it wrong again. This double bond is going to come over here, when it is going to come over here, the nitrogen exceeds its bond, hence there is no resonance, so there is no effect over here, there is no effect seen over here, so cross will come. Right, students? Hopefully you have been seen. Now here comes the chlorine. Now if you remember, chlorine basically, whenever there is fluorine, chlorine, bromine, they will have which effect? Minus I effect. Which effect? Minus I. I have already told you to put a star mark over here. Now comes, students, our next topic, that is the stability of now comes the next, that is the stability of resonating structures. Okay, if I talk about the stability of resonating structures, first of all, there are certain rules to learn for the stability. The very first rule is, whenever you are giving any uncharged species or you are giving a charged species, kindly put the stable mark to the uncharged one. So the uncharged species will be more stable than the charged one. 1 second, students. Okay, the uncharged the uncharged species, that means in which no charges are seen, will be more stable than the charged ones. The uncharged will be more stable than the charged species. Kindly keep this in your mind. Second thing, whenever you are seeing that both of the compounds have charged species, then on which factor the stability will depend? It will depend upon the pi bonds. More the pi bonds, more the stability. Second point is, more the pi bonds, more is the stability. More is the stability, students. Clear? Okay. Now, if you observe that yes, both of the species are charged, both of them have equal pi bond, then on which factor it depends? It depends upon electronegative. More electronegative atoms should have negative charge, while less electronegative atom should have positive charge. Which charge? Positive charge. More electronegative should have negative, while less electronegative should have positive charge. And for example, this is also fulfilled, then on which situation it will depend? There should be a separation. There should be a separation between the same charges. Separation should be there, and it should be more. Same charges, separation should be there. Now these are the basic rules that you need to remember while finding out the stability. Let us see the very first case. Now in this case, if I say this is my first, this is my second, kindly tell me which will have more stability. So first of all, check, do both have charged or uncharged species? Yes, it has charged. Yes, it has charged. That means both are charged. That means first rule is violated. Yes, charged it is. Now move to second rule. Second rule says that kindly check the pi bonds. Students, here it has 0 pi bonds, while it has 1 pi bond. So the more number of pi bonds, the more is the stability. That means the second one is stable than the first one. So you have to follow the rules step by step. Now let us see the next case. Now moving to this case, now what do we observe over here? This first one is what? It is uncharged. It is what? It is uncharged. While this is charged, second one. The third one is also charged. So as I told you, the uncharged ones are the most stable. That means first one is going to be the most stable. Now second and third, both are what? Both are charged. Now we will move towards the second rule. What is the second rule? Second rule says that count the number of pi bonds. In this, basically 1 pi bond is there. In this also 1 pi bond. That means second rule is also the same. Now moving to the third one, it says that more electronegative atoms should have negative charge and less one should have positive. So here if you see carbon and nitrogen. Nitrogen is more electronegative, having negative charge, while carbon carbon is having positive charge, and in this case nitrogen is having positive, but you know that nitrogen is more electronegative, so this will have, you know what, less stability, because more electronegative should have negative charge. So next order will come second, and then it will come third, because it follows the rule while it doesn't follow the third rule. Clear to you, students? Now moving to the next case, let us see the stability of resonance hybrid. When I talk about the stability of resonance hybrid, here also we follow some certain rules, just like resonating structures. The very first rule is large size conjugation is more stable. Large size conjugation is more stable, okay. For example, when you have 3 carbons or when you have 5 carbons, so the 5 carbons one conjugation is more stable than the 3 ones. Now comes closed conjugation and open conjugation. The closed conjugation will be more stable than the open ones. The closed conjugation is more stable than open one. Than the open one. And the last category comes as linear and cross conjugation, which we have already studied. So when we are going to see the linear and cross conjugation, the linear conjugation is more stable. Is more stable than cross one. So the linear one will be more stable than the cross one. These were the rules for resonance hybrid stability, students. Now let us make one structure and kindly tell me which one is more stable and which one is not. So if I draw a structure over here, this is CH2, then is double bond CH, single bond, you know, CH2, then is CH. Okay, I guess I have to take for alternative position. If I consider this case over here, let us see it as a positive charge. This is your first compound, okay. The next compound which I'm going to draw over here, it is basically CH2, again CH2 double bond CH, then we have again here CH double bond, you know, CH2. Okay, so this is our next case in this. Yeah, it is okay. CH2 single double single. Okay, now students, in both of the cases kindly check out. In this case, if I would see, what I'm going to see, this is common in both of these cases. What I need to see is in this conjugation what is happening. Either it can move in this direction or it can go in this direction, but in this case you know that positive charge is over here, so it will move in this direction, it will break in this direction. So what we are observing, this is unidirectional, basically this is moving in one direction, but this is not moving in one direction, this is not moving in one direction, students. It is a cross conjugation, it is a cross conjugation, while this is a linear conjugation. So which one will be stable? This one will be stable than the cross one. Clear? So this was all about the stability of what? Resonance hybrid, students. So yes, students, hopefully you have understood what is a mesomeric effect, what are the stability of resonating structure. There were certain rules you need to understand, and one by one you have to learn, like first is this, second is this, third is this. And similarly for the resonance hybrid also, basically there are 3 rules that you need to keep in your mind. Now we will move forward towards our next topic. So students, now we will talk about the applications of mesomeric effect. Now, as you all know, there are 3 kind of permanent effect. Number first is inductive, second is mesomeric, and third one is hyperconjugation. We will move forward towards hyperconjugation. But before that, if I'm going to compare these 3 permanent effects, what I need to keep in our mind is that if I ask about the stability, which is more stable in all of these 3 or in following compounds, if it is given to find out stability, which effect to be seen first? So first of all we need to see the mesomeric effect, then we have to see about the hyperconjugation, and at the last we have to focus on the inductive effect. So this we have to keep in our mind. Other than this, students, we need to keep in our mind about acidic strength. Basically what happens is acidic strength is directly proportional to minus m minus h minus I. Now here h refers to hyperconjugation, don't get confused, I am writing all of the 3 together, right? But they are inversely proportional to what? Plus m plus h and plus I. So basically this you have to keep in your mind while you are solving the questions based on the acidic strength. So students, all the applications just like we saw in the inductive effect, similar way is for the mesomeric effect. Now we will move forward towards our next effect, that is hyperconjugation. Now what do you mean by hyperconjugation? Basically hyperconjugation is permanent electronic displacement. What it is? It is permanent electronic displacement effect. Now listen to me very carefully. In inductive effect, what we saw polarization of sigma electrons. In mesomeric, what we saw, delocalization of pi electrons. Now here, in this case, in hyperconjugation, what we are going to see, we are again going to see basically the delocalization, but of whose? Of sigma electrons, not pi, of sigma. Here we are going to see the delocalization of sigma electron, students. Don't get confused. Again, I am telling you, if you want to write here, you can even mention this. What? That if I talk about inductive effect, that is I effect. Here I am going to see the polarization. That means poles are going to be made. Polarization of sigma electrons. And if I talk about which mesomeric effect, that is the M effect. Here I am going to see the delocalization of pi electrons in the conjugated system. And also in the conjugated system, do remember that. But when I talk about hyperconjugation, students, here I am looking forward towards the delocalization of whose? Of sigma electron. Now what is the basic difference between polarization and delocalization? Basically polarization creates a poles between the atoms, right? But delocalization refers to the movement. Okay, here we are going to see the movement of sigma electrons. Now what happens? Let us take a case to understand hyperconjugation in depth. If I take a case of, if I have this case with me, here is a CH3 attached. Now what happens, students, as you have seen in mesomeric effect, before explaining mesomeric effect, I told you about resonance. Similarly, if I'm going to ask you about what is hyperconjugation. First of all, I want you all to understand that basically what happens over here, there is two kinds of bond. One is single bond and another is double bond. If I observe, the bond length of the single bond present over here is 1.54 according to the benzene structure we have seen, or according to the structures which we have studied in the resonance type. But it should be 1.54, but it is not 1.54. It comes out to be 1.46. What happens? We know that this single bond should be 1.54 Armstrong, but it is not right. It comes out to be 1.46 Armstrong. Now you all would be wondering that why the bond length now is shortened. Why it is shortened? The question arises in our mind. The reason behind this is hyperconjugation. Now, how does hyperconjugation arises over here? We need to understand the two basic rules over here, that during hyperconjugation, first of all, we need to find the hybridization. Now, this carbon atom, here is carbon, here is also carbon. If I talk about this carbon atom, it is making two bonds over here with this carbon and two bonds with hydrogen if I complete its valency. To find out hybridization, we only count sigma bonds. We don't count pi bonds. So to count sigma bonds, how many sigma bonds it is making? It is making two with hydrogen and one with this carbon. That means total, how many bonds? 3 bonds. So I would say for 3 bonds, what is the hybridization? sp2. Clear? Now it has hybridization sp2. While if I talk about this carbon atom, it is making one bond with this, one bond with this. I'm talking about only sigma, not pi bond. Because in hybridization, we don't count pi bonds. So one with this, and one with the hydrogen atom again. So this is also which? This is also sp2 hybridized. But when I talk about this carbon atom, see, there you will observe that two carbons are sp2 hybridized, which is further attached to sp3 hybridized carbon atom. Now this carbon is what? This is sp3 because it is making 4 sigma bonds. So this sp3 hybridized carbon should have alpha hydrogen. Now there is a new term that I have being introduced to you, is alpha hydrogen. Now what do you mean by alpha hydrogen? Whenever you are observing a doubly bonded carbon, through that one carbon is directly attached. This doubly bonded carbon is further attached to a carbon which is sp3 hybridized, will have hydrogen. Now this carbon is basically alpha carbon. Why? Because it is attached to the carbon that is making a double bond. If it is an alpha carbon, then the hydrogen attached to this alpha carbon is known as alpha hydrogen. Now you're getting my point. The carbon which is attached to the carbon which is making double bond is alpha carbon, and the hydrogen attached to the alpha carbon are referred to as alpha hydrogen. Now here, if I talk about this carbon, students, it is what? It is alpha carbon. And if I talk about this hydrogen, these are 3 hydrogen, these are alpha hydrogen, these are alpha hydrogen. Now why there is a need to mention alpha hydrogen? Because what happens over here is, here delocalization of sigma electrons occur, in which case in carbon and hydrogen we observe delocalization. How? See over here. See over here, if I want to show the structure, first of all, I'm making it like this. Here is a carbon atom, here is carbon. It is bonded with hydrogens. It is bonded with hydrogen atoms. So let us make one hydrogen over here, second hydrogen over here. Now what happens, students? First of all, observe this very careful. There is a double bond over here, right? What we observe, that here there are 3 carbon atoms, but what we see that here now positive and negative sides are being built. Hydrogen here acquires a positive charge like this, and this is a negative. Now what is this structure? What is this structure? How can you break this bond? How can you break this bond? See, this is basically an imaginary structure. This is basically an imaginary structure that we are observing over here. Imaginary structure. Now try to understand it. What I have done is, I have separated the alpha hydrogen with the alpha carbon. That's it. Now what happens? This H positive is present over the region of this C negative only. It is present nearby the C negative only. Now happens what? Here happens conjugation. Here happens conjugation. And during conjugation, this negative charge will move towards these 2 carbon atoms, and this pi bond will be broken over this carbon. Now this you have already done in the resonance portion. So what structure do we obtain from here? From this we obtain that there is a double bond that is lying over here, and there is a single bond. Well, this bond is broken over this carbon, so this acquires a negative charge. Now I have just shown you carbon atoms for you to understand it very easily. Now here what happened? This negative charge came over here making a double bond, and this double bond is broken over this carbon, and when someone acquires a negative charge, someone acquires an electrons, it acquires a negative charge, so it got a negative charge. Now showing the hydrogens here. This is a hydrogen, this is a hydrogen. These two are hydrogen shown to you. Now what happened over here? We obtain a carbon double bond carbon system. We obtain a carbon double bond carbon system. So what happened over here is, there is a delocalization of sigma electrons. Basically, there was a sigma bond over here that was being broken, and it was and the electrons were seen moving in this direction. Why it was seen moving in this direction? Not in that, because we know that the electrons that are opened move from more towards less as these electrons are confined. So the movement according to the resonance will be in this direction, as you know. So what do we observe over here? We observe that basically what happens here, here is an imaginary structure being obtained, that is between an carbon and hydrogen. Why does carbon is doing such situation? To become stable. Okay, so this is all about hyperconjugation. If I ask you how many hyperconjugating structures can be obtained, or how much is it stable, so this all depends upon what? It all depends upon alpha hydrogen, because this alpha hydrogen is responsible for the delocalization of sigma electrons. This alpha hydrogen is responsible for delocalization. One second. Delocalization of sigma electrons. Okay, after that we see conjugation, and at last we obtain this as our product. Now students, there are some few points that we need to keep in our mind to see the stability. The stability of hyperconjugation, it depends upon what? It depends upon alpha hydrogen. More the alpha hydrogen, more the stable the compound is, more is the hyperconjugation observed over that. Now if I talk about the comparison between hyperconjugation and inductive effect, I would say the hyperconjugation effect is more dominant than the inductive one. If I talk about hyperconjugation and I talk about inductive effect. Why I am taking both of these cases, students? Because in both of these cases we observe what? Here we observe polarization of sigma electrons, here we observe delocalization of sigma electrons. In both of these cases we see the role of sigma electrons. That why I am taking these two cases. I am saying if we are given these both effects, then hyperconjugation is more dominant. Why? Because here delocalization occurs, here delocalization occurs of sigma electrons, while here only polarization, poles are made. You know the example of carbon 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 fluorine, here only poles are made. So here polarization of sigma electrons are observed, my dear students. Here polarization of sigma electrons occur. Clear now, students? We are going to see the next portion. Now we have covered all about hyperconjugation. Now you know what is hyperconjugation. Now you know what is basically the dominant factor, the hyperconjugated one or the inductive one. So students, the next topic under hyperconjugation is the systems in which hyperconjugation can occur. So now we are going to write the systems in which hyperconjugation takes place. Okay. Now students, basically there are three systems in which hyperconjugation occurs. One is alkene, second is carbocation, and third one is carbon free radical. Okay. I told you one is alkenes, the second one is carbocation, and the third one, students, is carbon free radical. Carbon free radical. Now we have already taken the case of alkenes. This one was the case of alkenes. This one. This we have already done of alkenes of alpha hydrogen, right? Now if I talk about the next case, that is of carbocation. Now what is carbocation? Carbocation is basically carbon plus positively charged species. So what we are going to see, carbon is attached to a positively charged species over here. Now this carbon is attached to positively charged species over here. Now see what happens. Now let us consider this as a positively charged species. So this carbon is now referred to as alpha carbon. See, here we are taking double bond. So this is our alpha carbon. Here we are taking positive charge. So this is our alpha carbon. If students, this is our alpha carbon. So now what are alpha hydrogens? Alpha hydrogens are the one that are attached to the alpha carbon. So this hydrogen and this hydrogen are basically what? They are basically alpha hydrogen, which will be responsible for what? They will be responsible for hyperconjugation. More the alpha hydrogen, more will be the hyperconjugation, more will be the stability. Clear? Now if I talk about carbon free radical, again the same case arise. For example, this is CH2, it has a radical. Now it is attached to a carbon. Now this carbon through which it is attached, this radical is attached to a carbon. This carbon will be referred as alpha carbon, and now the alpha hydrogens will be the one that are attached to whom? Alpha carbon. Now these all are what? Alpha hydrogen. So these are the three systems in which hyperconjugation occurs. Now students, one is the case you all would be wondering, ma'am, you have discussed about alkenes, you have discussed about carbocations, you have seen carbon free radical, why not carboanion? Why not carbanion? Now students, in the case of carbanion, let us make this case and understand why does hyperconjugation do not occur over here. To make this, first of all, we know that, for example, this is our carbanion. It is attached to a carbon. Here are the hydrogens, right? Now what we will observe over here, again, like I was talking about alkene, so double bond that is attached to a carbon is alpha carbon, radical that is attached to a carbon is alpha carbon, or positive charge that is attached to a carbon is alpha carbon. Here negative charge that is attached to a carbon is alpha carbon. If this is alpha carbon, what are the alpha hydrogens over here? So you would say, ma'am, these are alpha hydrogens. Okay, now I will consider only one of the alpha hydrogen for the hyperconjugation to occur. How I am going to observe this, students? How I am going to observe this? See, if I am going to see about this hydrogen atom, what I am observing, it already has a negative charge. Here is hydrogen, here is hydrogen. What happens? Hydrogen is positive and the carbon requires negative. Now this is the imaginary system like we did in alkenes case. Now what happens? What happens, students? Kindly listen very carefully. Here is a negative charge, here is a negative charge. Repulsion occurs between two negatively charged species. Now here what happens? Here what happens? Repulsion occurs here, leading to destability. That means it is not at all stable. If it is not at all stable, that means there is no hyperconjugation. So there is no hyperconjugation, in what? In carbanion. Clear, students? So only 3 systems are there in which hyperconjugation takes place. Now students comes, what are the conditions for hyperconjugation to occur? What are the conditions for hyperconjugation to occur? Okay, the very first condition is alpha carbon should be present. Because if there is no alpha carbon, then there will be no alpha hydrogen. So alpha carbon should be present. Second thing, alpha hydrogen, at least one alpha hydrogen should be present. Clear? So these are the conditions that are required for hyperconjugation to take place, students. Now we are going to calculate, you know, how many alpha hydrogens are present in each of the cases. Okay, now we are going to do the calculation for alpha hydrogen. You need to calculate how many alpha hydrogens are present in every particular case. Okay, I am taking the first case, CH3 CH triple bond CH2. No, basic, very sorry. In alkenes it takes place. I have written by chance alkynes. Okay, so kindly make this as a double bond. Yeah. Okay. So I've given you the first very example of an alkene. Now kindly tell me how many alpha hydrogens are present. So you know, as in the case of alkene, this carbon and this carbon is making a double bond, right? So the carbon attached with the doubly bonded carbon is referred as alpha carbon. This is the alpha carbon. These two are basically what? These two are sp2 hybridized. The previous case which we have done is the same case, right? So these two are sp2 hybridized. The carbon which is attached over here is sp3 hybridized, which is alpha carbon, which is attached to a carbon which is doubly bonded, right? The double bond lies in between these two, so these two won't be considered. But the carbon attached to these two are alpha carbon. Now the hydrogens which are attached with this carbon are alpha hydrogen. How many hydrogens are attached over here? 3. So here how many alpha hydrogen will be there? Alpha hydrogen will be 3. Hope so it is clear to you. Now let us take one more case. Okay, now this is your case, students. Here I have shown you the bond line notation. If you are being confused that what it is, kindly convert it into condensed structural formula or the expanded one. So what I'm going to do is, it basically is like this. To make you understand, it basically is like this. It is basically like this. Here is CH3, here is again CH3, here is CH3. If I open this structure, it looks like this, right? This is the carbon, 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 in such a way. Now again I ask you how many alpha hydrogens are present over here. So you would say that this is carbocation and the carbon attached with this carbon is alpha carbon. Now, how many hydrogens are present with alpha carbon are alpha hydrogen, but this alpha carbon has no hydrogen because they are further attached with carbon atoms. They are not at all attached with any of the hydrogen. Kindly listen again. Whenever you are talking about double bond, carbocation or free radical. The carbon attached to them is alpha carbon. So the hydrogen attached to them will be alpha hydrogen, not the another ones. So here this is alpha carbon. It should have hydrogen to be referred as alpha hydrogen, not the another ones. So there is no alpha hydrogen over here. That means 0 alpha hydrogens are present over here. Right? Now let us take one more case. See this case now. Kindly convert it into bond line notation if you are feeling it is quite tough. So it is basically like this. CH2 double bond CH2, right? If I open up this structure. Now what happens over here? These two are sp2 hybridized. The carbon that will be attached to these two will be alpha carbon, but there are no carbon attached to these two. So there is no, if there is no alpha carbon, so there will be no alpha hydrogen. See, this is only the version of this, just it is, being removed and it is shown to you. Right? So if there is no alpha carbon, there will be no alpha hydrogen. Now if I take the fourth case for you, the fourth case is this one. Carbon, carbon, hydrogen, CH3, hydrogen, CH3. If I ask how many alpha hydrogens are present over here, so what you will say? Ma'am, these two both are alkenes. This is basically alkene, the doubly bonded carbon. The carbon attached to these doubly bonded is alpha carbon. The carbon attached to this is alpha carbon. Now, alpha hydrogen are the ones that are attached with alpha carbon. Alpha hydrogens are the one that are attached with alpha carbon, not these two. They are not attached with alpha carbon. Kindly see this. Alpha carbon, alpha hydrogen are the one that are attached with alpha carbons are only considered, not the another one. So how many alpha hydrogen? Basically there are 6 alpha hydrogens present over here. So it was quite easy for you to understand, right? Now let us take one more case. See this case. Okay, if I give you this case, students, then how many alpha hydrogens are present over here in this case? First of all, see, this is carbon, carbon double bond carbon. The carbon attached to these two both will be referred as alpha carbon. So I would say here is one carbon, here is one carbon, here also, here also. These 4 are alpha carbon that are directly attached to the doubly bonded carbons. That means students, what happens over here? If I complete the valency of these carbon, it is CH3, it is CH3, it is basically CH2, it is basically CH2. So how many alpha hydrogens are present over here? 3 plus 3, 6. 6 plus 2 is 8. 8 plus 2 is 10. How many alpha hydrogens? 10 alpha hydrogens are present over here. Clear? Okay. Now let us see one more structure. If I have this with me, how many alpha hydrogens are present over here? So what you will say? This carbocation is attached with the carbons. Now these carbons are referred as alpha carbons. Now how many hydrogens are attached with these carbons? See, this is making only a single bond. So 3 bonds are left. 3 hydrogen will come. Similarly in this way. So these hydrogens are alpha hydrogens and hence it comes out to be 6 students. Okay. Now let us take one more case. Now, if I talk about this case is quite different and I want you all to answer it in a very good manner. Kindly tell me how many alpha hydrogens are there. Some of the students will do correct if they listen to me very carefully. I told you carbanion does not show hyperconjugation. So directly you will write it shows 0 alpha hydrogen. Do not start making carbons and count. No. You know only 3 systems are responsible for hyperconjugation. Rest carbanion is not responsible for hyperconjugation. So it won't exist. My dear students. Now hope so it is clear to you. Now comes the next case. For example, if I ask you about this case, how many alpha hydrogens are present? So you would say, ma'am, it is only a carbocation. It is not attached with any of the alpha carbon. So there is no alpha carbon. When there is no alpha carbon, so there is no alpha hydrogen. Clear, students? Now let us take one last case and we'll move forward towards our next topic. Okay, now here is a radical. How many alpha hydrogens are present over here? So you would say that these are attached to these carbons. If I complete its valency, It's basically like this. So these are alpha carbons. So hydrogen attached with them are alpha hydrogens. So it will be 3 plus 3 plus 3. That means 9. That means alpha hydrogens are 9 that are present over here. Clear? Now you are able to identify alpha hydrogens, alpha carbons very clearly. Now comes the concept of stability of carbocation, carbon free radical, and alkenes. It all depends upon what? The stability of carbocation, carbon free radical, and our alkenes. All of these stability, they directly depend upon alpha hydrogen. More the number of alpha hydrogen, more will be the stability. Now I'm taking certain cases for you to understand. Okay, if I take the very first case 1 for carbocation. If I take the case for carbocation, now this is your very first structure which I'm going to make over here. Okay. Okay. Now kindly tell me which of the following structure will be more stable. You need to calculate what? Alpha hydrogens. So now let us calculate alpha hydrogens in all of these cases. See, this is the carbocation. It is attached to this carbon, and this carbon. So these are alpha carbons. Now hydrogen attached with them will have alpha hydrogens, right? So how many hydrogens with them? If we'll complete the valency, we have 3 plus 3, 6. 6 plus 2 is 8. So we have total 8 alpha hydrogens over here. Now if I talk about this case, there is one carbon, these are the alpha carbons. The hydrogens attached with them are alpha hydrogens. How many? 1 plus 3 is 4. So alpha hydrogens are basically 4 over here. If I talk about this case, students, here only one is alpha carbon because it is directly attached to this only, and it has 2 hydrogens with it. So here there is alpha hydrogen is 2. So more the number of alpha hydrogens, more will be the stability. So the order comes out to be this. That means what it is 3 degree. What it is 2 degree. What it is 1 degree. So all I would say in the case of carbocation, 3 degree is more stable than 2 degree and then 1 degree. Kindly keep this in your mind. Clear, students? Now if I compare the stability of alkenes, like I compared the stability of carbocation, in the stability of alkenes also we are going to see the same case. Stability of alkenes. See, whenever you find there is same number of alpha hydrogen, for that case I would just say, after seeing the hyperconjugation concept, kindly move to the inductive effect. Okay, when there are alpha hydrogens same, then move towards the inductive effect. That's all. Now if I talk about the stability of alkenes, the very first case that I'm going to show you over here is, start calculating alpha carbons and then alpha hydrogen over here. This is your A. Okay, start calculating along with the double bond. You need to see the alpha carbon, then you need to see the alpha hydrogens. Now for the next case, this is your second case, students, which is referred as B. Calculate alpha hydrogen over here also. Now comes your third case. This is your third case, which is C, and comes your last case. Or okay, just take this 3 cases. No need for the decompound. I ask you the order of stability. So what will be the order of stability here? This is alpha carbon, alpha carbon, alpha carbon, alpha carbon. The hydrogen attached with them are alpha hydrogen. So 3 plus 3 6, 6 plus 3 9, 9 plus 3 is 12. So how many alpha hydrogens are there? 12. If I take this case, how many alpha carbons? This is alpha carbon, this is alpha carbon, this is alpha carbon. So how many hydrogens here? 3 plus 3, 6. 6 plus 3 is 9. Alpha hydrogens are 9. Do not count this hydrogen because it is not attached with alpha carbon. Do not count this. Now, if I talk about this case, here we have this carbon as our alpha carbon and this carbon. These two don't have any alpha carbon. How many alpha hydrogen again? 3 plus 3 is 6. So, alpha hydrogen comes out to be 6. So, more the number of alpha carbons, alpha hydrogens, more the number of stability. So, here it has more alpha hydrogen than this. So here it will be A will have more stability, then B, then will come C. So hope so it is clear to you all about stability of alkenes. Now comes the stability of free radical. Now comes the stability of free radicals. Okay, if I talk about the stability of free radicals, let me say this is your A molecule. Let us say this is your A molecule. Now coming towards the B molecule, let us say this is your B molecule. Now if I ask you about this C, this is your C molecule. Which one is more stable? Again, you need to find out what? Alpha hydrogens. So here the carbons that are attached to the carbon free radical are alpha carbon, alpha carbon, alpha carbon. How many alpha hydrogen? 3 plus 3 plus 3. That comes out to be 9. That comes out to be 9. If I talk about this concept, we have these two as our alpha carbon. So hydrogen attached with them will be our alpha hydrogen. So 3 plus 3 is 6. Again, alpha hydrogen comes out to be 6. Now if I talk about this case, this radical is attached to this carbon which has 3 alpha hydrogen with us. So here how many alpha hydrogen comes out to be 3. So what will be the order of stability? It will be this, because the stability depends upon the number of alpha hydrogen, students. Hope so it is clear to you, students. So this ends our effects, students. Before the effects, this ends our permanent effects. Now comes the last effect, that is the temporary effect, which is electromeric effect. Kindly remember, it is a kind of temporary effect. It occurs only in the cases of multiple bonds. In the cases of multiple bonds. Now students, here displacement of pi electron occurs only. Now you need to remember that in inductive we talked about polarization of sigma electrons. In mesomeric we talked about delocalization of pi electrons. In hyperconjugation we talk about delocalization of sigma electrons. Now coming towards the electromeric, we will talk about what? Pi electrons, but only displacement, right? Other than this, students, it occurs only in the presence of attacking reagent. For example, I have this as my reactant molecule, which is CH2 double bond CH2. Ar is referred to as the attacking reagent, in which presence it is being occurred. When you remove the attacking reagent, the reaction will stop. That is why it is known as temporary, because it will occur only in the presence of attacking reagent. Till we have the attacking reagent with us, the reaction will proceed. If we don't have, the reaction would stop. Now what happens over here, when attacking reagent is present, it splits into, one will acquire a positive charge, another will acquire a negative charge. In such a way. Similarly, in the case of carbonyl compounds also, you can observe these kinds of stuff where oxygen acquires negative charge and carbon acquires positive charge, right? So this was the electromeric effect. So here we end our effects, electronic displacement topic. Now student, I am moving towards the next topic, which is aromaticity. I hope so you know aromaticity before this also, but still we need to do aromaticity in detail. What is aromaticity? Basically, there are conditions for a compound to be aromatic. What are these conditions? The compound should be cyclic. Number first, it should be cyclic. Second thing, there should be conjugated system. Now you have done conjugated system in a very depth. We have covered basically 5 cases and 1 special case, if you remember, in the mesomeric effect. In the resonance topic, we have already done what are the conjugated system. So now you are able to identify what are conjugated. You know what a cyclic system. Cyclic is the one which is making a ring, in which first carbon is attached to the last carbon atom. That is cyclic system. Other than this, what are the conditions for a compound to be aromatic? It should be planar. It should be planar, students. The molecule should be planar. Basically, it should be sp2 hybridized. Other than this, students, it should follow Huckel's rule. it should follow Huckel's rule. Now, what is Huckel's rule? It is 4n plus 2 pi electrons. It is this rule. Now, here n value can be 0, 1, 2, 3, and so on. So, if you put n value 0, 1, 2, 3, 4, you are going to get the pi electron system. So, you need to calculate how many pi electrons are present, and if it follows this rule, it is said to be as aromatic. And these four are the basic necessity conditions for a compound to be aromatic. Okay, now let us take one example. If I talk about this case, yes, it is cyclic because the first carbon is attached to the last carbon atom. Okay, it is a conjugated system. Why? Because see, A double bond B, C has a positive charge over it, so it is a conjugated system. Other than this, it is a planar system. You can also check the hybridization over here. Now I talk about Huckel's rule. Does it follow Huckel's rule? So you can check over here how many pi electrons are there. 2 pi electrons are there, right? Single bond contain 2 electrons, so single pi bond has 2 electrons, right? One pi bond has 2 electrons, so if it has 2 electrons, we need 4n plus 2 should be equal to 2, because it should be equal to the value of these electrons. So what should I put here? N value, so that it is equal to 2. N should be 0, so hence it is satisfying. 2 is equals to 2. That means it is following Huckel's rule. So that means it is an aromatic compound. So hope so now you are able to identify what is an aromatic compound. Other than this, students, you can also take the case of benzene ring. Now if I talk about this benzene ring, first of all, you need to check that it is cyclic. Yes, it is cyclic. Then you need to check it is planar. Yes, it is planar because it is sp2 hybridized. Then you need to check the conjugated system. So yes, we are having conjugated system. How come? A double bond B, single bond C, double bond D. So it is a conjugated system. Yes, it is a conjugated system. Yes, that's correct. Now, does it follow Huckel's rule? You have to count the electrons. Basically, there are 6 electrons over here. So, you have to make 4n plus 2 should be equal to 6 electrons. So, if you put n value as 1, it is equivalent. 6 is equals to 6. That means it is following Huckel's rule. So, benzene is an aromatic compound. Students, aromatic compounds are further categorized into benzenoid and non-benzenoid. Benzenoid are the ones in which benzene rings are present. Non-benzenoid are the one in which benzene rings are absent. Now comes the next category, that is anti-aromatic. Now, for a compound to become anti-aromatic, it should again follow some certain rules. And the first rule is same. It should be cyclic. It should be cyclic. The second condition, again, it should be planar. The next condition, it should have conjugated system. It should have conjugated system. We require these basic necessity conditions. But here, Huckel's rule is not followed. Here, which rule is followed? Here, 4n pi electron system is observed. Which system? 4n pi. So here, the value is becoming equal. But there will be certain cases. For example, if I talk about this case, let us calculate the value of pi electrons over here. There are 2 pi bonds. That means one bond contains 2 electrons. 2 will contain 4 electrons. So we want 4 electrons. Kindly put the value is equal to 4. Is it possible? No. It will never come out to be 4. Because if you'll put n value 0 here, then it will come out to be 2. If you'll put n value 1 here, it will come out to be 6. So it does not follow 4n plus 2. But does it follow 4n system? Yes. If you put n value as 1, it comes out to be 4 pi electrons. Clear? So here it is an example of what? Anti-aromatic system. The basic difference between these two both are what? There was 4n plus 2 system. There is 4n system. That's it. Now comes the non-aromatic ones. If I talk about the non-aromatic ones, basically they are the odd electron system, and they are the one that does not follows anti-aromatic or aromatic, which disobeys aromatic as well as anti-aromatic, which does not follows both of them. They are referred to as non-aromatic system. Clear, students? So these are basically odd electron species. Now if I give you certain cases to identify, the very first case is this one. Kindly identify which of the following compound is this. So how you'll identify? Yes, it is cyclic. Yes, it is planar. Yes, it is conjugated. But how many pi electrons are present over here? 2. See, how 2? Because it has one sigma, one pi bond, so 2 pi electrons. Does it follow Huckel's rule? What is Huckel's rule? 4n plus 2. Huckel rule is 4n plus 2. If I put value of n here as 0, n here as 0, what it comes out to be? 2 pi electrons? Yes. So we need 2 pi electrons only. Hence it is aromatic. It is what? It is aromatic system. Okay. Now let us take one more example. Okay, if I take this example, students, kindly tell me which system is this. Now, here when you are counting the pi electrons, you will see 1, 2, that means one pi bond contain 2 electrons. So 2 electrons, 2 electrons, 4 electrons. Now don't count all of these electrons. The one that are responsible for resonance or conjugation will be counted. So these will be responsible, not these ones. So 2 plus 2, 4, 4 plus 2 is 6. 6 electrons. How many? 6 pi electrons are responsible. Now if I put in this formula, 4n plus 2, n value as 1, I get 6 value. Yes, I am getting the same number, 6 pi electrons. So hence it is aromatic. It is also aromatic. And yes, other conditions are also being fulfilled over here. That it is cyclic, it is planar, it is conjugated system. Other than this, if I give you one more case. Okay, if I give you this case, how many pi electrons are present over here? So you would say that, ma'am, here 2 pi electrons are present. Okay, but all the atoms are sp2 hybridized? No. What do you observe over here? It is sp2, it is sp2, but it is sp3 hybridized. Right? So here, do you observe any conjugated system? No, there is no conjugated system. There is only double bond given. When there is no conjugated system, that means there is no aromatic, there is no anti-aromatic. So it will be what? It will be non-aromatic. It will be what? Non-aromatic. So these are the systems that you need to consider. One, let us take one more example. Okay, if I take this case, now I am taking negative charge over here. How many pi electrons? 2 here and 2 here. 4 electrons. Now 4 pi electrons are only seen in the case of anti-aromatic. So this is a case of what? Anti-aromatic system. Now you are able to distinguish between aromatic, anti-aromatic, right, and non-aromatic. Now comes, students, about the stability. What do you mean by the stability? Which is more stable? Aromatics are the one which are more stable. Then comes the non-aromatic ones, and at the last comes the anti one. Aromatic comes the first, then comes the non-aromatic one, and at the last it comes anti-aromatic system. Right, students? So this is the stability order that you need to keep in your mind. So yes, students, moving forward to our next topic, that is the application part over here. Application, we can see that we can observe about dipole moment, we can learn about dipole moment, we can learn about bond length. So these come under the application portion of aromaticity, that we are able to calculate about bond length, dipole moment, with the help of aromaticity. We can calculate both of these very easily. For example, if I say you one system, you know that how to calculate, you need to calculate the stability order. You know aromatics are the one which are more stable, then comes the non one, then comes the anti one. So whosoever compound is being given to you, kindly use in such a situation. For example, if it is given to you like this is your first compound, this is your A compound given to you, and the B one which is given to you is somewhat like this. Okay, they are asking you which is more stable. So first of all, identify, first of all, students, one second. Okay, first of all, students, identify over here which is aromatic and which is non-aromatic. One second, let me count the electrons. I guess I have to. Yes, here pi bond will come. So if I ask you about which of the following cases will be more stable, so what you need to do is you need to break this double bond first. When you will break this double bond first, you are getting charges. When you are getting charges, what do you observe over here? You observe that this double bond is break over oxygen. So oxygen requires negative charge. This carbon requires positive charge. In this case, what is going to happen? In this case also, the oxygen gets the negative charge while this carbon gets the positive charge. Now what happens, students? Which is this this case, this is aromatic case, and if you see this case, this is anti-aromatic case. So we know that aromatic are the ones which are more stable than the anti-aromatic ones, so this will be stable. So you need to break the bond in some of the cases, like if it is given to you, right, my dear students. So this was the application portion that we have covered over here. Now students, we will move forward towards the next topic, that is heat of hydrogenation. What do you mean by heat of hydrogenation? Basically, it is amount of energy that is released in any reaction. So what happens? It is the amount of energy that is released. It is the amount of energy that is released during the reaction. Now, if I take an example, we have taken any alkene molecule in the presence of, it is reacted with H2, and it is a surface phenomena. In the presence of nickel, it is occurring. So you will observe this in surface chemistry as well. So what happens over here is, over here, 1,1 hydrogen, this pi bond breaks down and 1,1 hydrogens are attached over here. So what happens? It comes out to be like this. It comes out to be like this, CH, single bond CH. And here heat is released. So it comes out to be, delta H comes out to be negative because heat is released. Now this heat which is released is known as heat of hydrogenation. This is known as heat of hydrogenation that is being released. Now students, what happens? The heat of hydrogenation depends upon number of pi bonds here, because it is occurring in alkenes. So heat of hydrogenation depends upon number of pi bonds. Directly it depends upon this, but indirectly that means inversely it depends upon the stability. Inversely it depends upon the stability. So you need to keep this in your mind as well while solving some of the question, that if there are more number of pi bonds, then there will be more heat of hydrogenation. Now similar to heat of hydrogenation comes heat of combustion. Amount of energy released during complete combustion of hydrocarbon. Amount of energy released during complete combustion of hydrocarbon. So that is basically known as heat of combustion. Now if I write the combustion reaction, it is basically, let us take a general reaction in which CX, HY, X and Y can be the numbers, which is reacting with O2. Okay, which is reacting, if you will balance out here, it comes out to X plus Y by 4. If you're going to balance it out, okay, it comes out to be, combustion reaction takes place in the presence of O2 molecules. Now what comes over here? X CO2 is produced over here, then Y H2O is produced over here, Y by 2 H2O. And yes, again, amount of energy that is being released here comes out to be negative. Now this which comes out to be negative is heat of combustion. This is what? Heat of combustion. This is what? Heat of combustion that is released during the combustion reaction. Now students, it depends upon number of carbon. It depends upon number of carbon, because here X is the number of carbon atoms, right? So heat of combustion, it directly depends upon number of carbon atoms and it inversely depends upon the stability, right? So this was all about heat of combustion. Now you know about heat of hydrogenation and you know about heat of combustion. So students, proceeding towards our next topic, that comes out to be the reaction intermediate. See, when I started this chapter, I told you we will cover first electronic displacement. That means we are going to cover first about substrate, right? Then we are going to see about the next attacking reagent, which we are going to see, don't get worried, it will come after this topic. And then we are going to see the intermediates. Basically intermediates are the one which are carbocations, carboanions, free radicals. In between also I have given you general introduction of carbocations, carboanions and carbon free radical. So what are carbocations? Again, carbocations are basically carbon plus positively charged species. Carbon plus positively charged species. So that comes out to be carbocation, and I took an example of CH3F also. If you remember, I told you that when there is a heterolytic cleavage over here, what do we observe? We observe CH3 positive and F negative. Because fluorine is more electronegative than carbon, so it acquires a negative charge, and carbon acquires a positive charge. Now what happens over here? This CH3 positive is basically what? It is basically carbocation. This is the carbocation generation. This is the carbocation generation, students. Now, if I talk about carbocations stability, I would say the first application that we observe over here is alpha effect. If I talk about stability of carbocation, then we observe about alpha effect. What do we observe? We observe alpha effect. Now, what do you mean by alpha effect, students? Basically, alpha effect are the ones, if I'm talking about any atom A that is attached, for example, any atom A that is attached to the carbocation. Okay. Now, this A basically carries a lone pair on it. If it carries a lone pair on it, then we know according to the resonance, the lone pair will break over here. And when the lone pair will break over here, what are we going to get? We are going to get carbon double bond A and both of these hydrogens. And when this carbon positive is getting electrons, so it will become neutral, while this A is giving its electrons lone pair, so it will acquire a positive charge. This we have done in resonance. So in these, both of these structure, which will be more stable? This will be more stable. This will be more stable than this structure. So here, this is alpha effect. Alpha effect is the effect that this carbocation is attached to an atom. This atom is basically the alpha atom. So it produces an alpha effect here, which we observe that the other resonating structure is more stable. So whenever you are talking about stability, you have to see alpha effect first, then aromaticity, then mesomeric, then hyperconjugation, and then is inductive. So what you need to see for the stability, first of all, you see the alpha effect. Then afterwards, you need to see what? Afterwards, you need to see the aromaticity. These are the rules. Then you need to see the mesomeric effect. Then you need to see the hyperconjugation. And at the last, you have to see the inductive effect. Now, if I talk about the stability order, if I talk about the stability of carbocation, so you know that, students, basically 3 degrees more stable, then 2 degree, then 1 degree. Other than this, what is the stability order? It depends directly upon plus M plus H plus I, plus M plus H or plus I, and inversely it depends upon minus M minus H minus I. So this is the stability I'm writing like this. This is the stability order for carbocation that you need to keep in your mind. Okay. Now, students, comes our another topic under the category of carbocation, that is the properties of carbocation. What are the properties? It is sp2 hybridized. It is basically sp2 hybridized. Other than this, its structure is trigonal planar. Its structure is trigonal planar. Right, students? Other than this, what do we observe over here? It is diamagnetic in nature, and it has a magnetic moment 0. It is diamagnetic and magnetic moment is 0. It is diamagnetic in nature. Students, how does it works out? It works out as an electrophile, as an electron loving species. So it works out as an electrophile. What are electrophile? Phile refers to as loving, electro refers to as electron. So those who are electron loving are referred to as electrophile. So carbocations are the one that are electron loving. That's why it is having a positive charge, because it is attracted towards the negative ones, right? These are also known as Lewis acids, students. These are also known as Lewis acids. Clear? So this was all about carbocations. Now moving to the next reactive intermediate, that is carboanion. Now if I talk about carboanion, again I would say that carbon plus negatively charged species. Carbon plus negatively charged species. This is what? This is carboanion. This is what? This is carboanion. For example, I have taken a case of like the one which is acquiring a negative charge. In other words, I would say here also, students, I want to ask you the effect. Which effects do you observe? Again, the concept is same. To check the stability, we need to check first the alpha effect, then comes out to be your mesomeric, hyperconjugation, and then the inductive one. Or you can directly write aromaticity also after the alpha effect, right? Other than this, what is the stability of carbanion? Other than this, the stability of carbanion is 1 degree is more stable than 2 degree, than is 3 degree. Okay, other than this, one more stability order that we need to keep in our minds. Stability of carboanion is that it is directly dependent upon minus m, minus h, minus I, and inversely upon plus m, plus h, and plus I effect. So you need to keep in mind these stability orders whenever you are studying about carboanion. Other than this, students, as we have seen in the carbocation here, what are the properties? The properties are it should be sp3 hybridized. Again, students, here it should be trigonal planar. It should be okay. Other than this, students, it should be again, it should be, it should act in the previous one. We have seen it as a Lewis acid, but this is a Lewis base. It is also magnetic. It is Lewis base. It is diamagnetic. So these are the properties that we observed in what? Carboanions. And it also acts as a nucleophile. In the previous case, we saw the carbocations were acting as electrophile. These are acting as nucleophiles. Clear? So these are the properties of carboanions. Now comes the next reactive intermediate, that is carbon-free radical. Now students, if I look towards the free radical case, carbon free radical, basically it is almost the same as that of carbocation. As we have seen in carbocation that 3 degrees more stable than 2 degree than 1 degree. Similarly, if I talk about the free radical basically is like this, right? So if I talk about free radical case, that means which have one electron over it, the stability order is same as that of carbocation. The stability order for free radical is again 3 degree will be more than 2 degree, and then comes the 1 degree. This is going to be same as that of carbocation. Now after the students, if we need to compare between the carbon free radical effects, we need to see the effects are going to be in the same order. First we have to see mesomeric effect, then we have to see hyperconjugation effect, and at the last we have to see inductive effect. Now if I talk about effect stability, so first we are going to see the mesomeric one, then the hyperconjugating one, and at the last the inductive one. So this order, I guess, after so much of the concept learning, you have already learned this, that first of all you have to see mesomeric, then hyperconjugation, and at the last inductive. After this, students, come the stability with respect to mesomeric, with respect to hyperconjugation and I, which will be plus I minus I. So it is same as that of carbocation. Again, if I talk about the stability of carbon free radical, comes out to be that it is directly proportional to plus m plus h plus I, while it is inversely proportional to minus m minus h and minus I. Clear? It is same as that of carbocation. Other than this, students, if I talk about the free radicals property, if I talk about its properties over here, so it is sp2 hybridized. It is what? It is sp2 hybridized. It is paramagnetic in nature. It is sp2 hybridized. It is paramagnetic in nature. The previous two were diamagnetic in nature, but yes, it is paramagnetic in nature, and students, it act as an electrophile. It act as electrophile. Other than this, students, it is neither Lewis acid nor Lewis base. It is neither Lewis acid nor Lewis base. Clear, students? So these are the properties of free radical. Now we are going to start our next topic, that is going to be types of attacking reagent. Now students, proceeding towards our next topic, kindly correct in the previous one in carbanion. I've told you trigonal planar. It is basically pyramidal in shape. It is basically pyramidal. So kindly correct this. Okay, now moving forward towards our next segment, that is going to be types of attacking reagent. Types of attacking reagent. Now, if I talk about the types of attacking reagent, basically these depends upon the substrate on which it is going to attack. As I've told you in the very start of the chapter, that substrate basically depends upon one category, that is electron density. If it has electron density more, then the attacking reagent which is going to attack will have less electron density. And if the substrate have less electron density, then the attacking reagent which is going to attack will have more electron density. Now there are two kinds of attacking reagent that we are going to study over here. One basically is electrophile. One basically is electrophile, and the another one is basically nucleophile. And the another one basically is nucleophile. Now students, if we start from the very first, that is electrophile. The very first, that is electrophile. What do you mean by electrophile? The name itself says phile refers to as loving. Phile refers to as a loving species. Now, electro refers to as electron. So, in other words, I would say that electron loving species are electrophile. And if someone love electrons basically are what? They are negatively charged. So who will love negatively charged? Which is already a positive or a neutral species. That means electrophile can be positively charged species. It can be positively charged species because it loves electrons. It wants electrons to get attracted. That means it should be positively charged species. Or it can be the neutral ones. It can be the neutral species also. Okay, so the very basic thing that we got from the name itself is electron loving. Other than this, what we got, that it is a positively charged species. Other than this, what we got, it is neutral species. Now comes the examples for positively charged species as well as the negatively charged species. Now, examples of electrophile. As I told you, electrophile are basically of two categories. One is the positively charged one and another one is the neutrals one. These are basically electrophiles. Now, if I talk about the positively charged one, they can be H positive, it can be H2O positive. These all lies under the H3O positive, sorry. It lies under the category of positively charged species. Other than this, I can say Cl positive. Okay, you can take further more example. For example, I positive, CH3 positive. So these are basically the examples of positively charged electrophiles. If I talk about neutral electrophiles, it can be AlCl3. It can be FeCl3. FeCl3. Other than this, it can be SO3. It is C, not D. Okay, kindly correct this. Let me write it again. FeCl3. Then I have told you about SO3, right? So these are the examples of neutral electrophiles. Now students, come the next category, that is going to be nucleophiles. The second one comes about nucleophiles. Now, as I've already told you, what is philes? Philes refers to as loving. Philes refers to as loving. This refers to as loving. Now, what is loving over here? Nucleus loving. Now these are the one that are nucleus loving species. Nucleus loving species are nucleophiles, students. Now they can be negatively charged or can be neutral. They can be negatively charged. Okay. Very sorry, students. Okay. They can be negatively charged or neutral. Why they are negatively charged? The question arises because they are nucleus loving. Nucleus is positively charged species. So, which is negative that will be attracted towards positive, or which is neutral that will be attracted towards positive. Now, students, come the examples of nucleophiles. If I talk about examples, first of all, I am talking about negatively charged one, and then we will talk about what? Neutral ones. So if I talk about the negatively charged one, it can be Cl negative, Br negative, OH negative. These all lie under the category of negatively charged. Other than this, you can take cyanide group, that is Cn negative. Okay. Now, if I talk about neutral ones, it is NH3. Lone pair of electrons is present over here. Then H2O. Okay. Other than this, I would say RNH2. Right, students? So these are the examples of neutral species, and one more you can take ROR also over here. Now these are the examples of nucleophiles. Now comes the next category. There is also one category known as ambiphiles. It is what? It is ambiphile species. The third category is ambiphiles. Now, ambiphiles, philes again is loving. Ambiphiles refers to the one which can act as electrophile also and nucleophile also. So all I would say is which act as electrophiles, as well as nucleophiles, Clear, my students? Now, if I take an example of this, let us take an example of carbonyl compound over here. This is our carbonyl compound, C double bond O. Now, if I say there is an electrophile that attacks over the species, if electrophile is attacking over the species, then it will act as a nucleophile. When it will act as a nucleophile, what is going to happen? If it is electrophile is coming to attack over here, then these lone pair of electrons will attack with this and the product will form. But if there is a nucleophile that is attacking over here, if there is a nucleophile attacking over here, then this species act as an electrophile. Okay, so it depends upon the attacking reagent which is acting. Now, when nucleophile is attacking over here, it will attack over the carbon atom. Kindly consider this. It will act over the, if this is nucleophile, it will attack over this carbon atom. But when it is electrophile is attacking, it will attack over the oxygen atom. So this is a very kind of different concept that you got to know it. Ambiphiles, it can act as electrophile, nucleophile, depending upon the attacking reagent. If the attacking reagent is electrophile, it will act as a nucleophile and it will act on oxygen atom. If it is nucleophile is coming to attack over this species, then this will act as electrophile and it will attack on the carbon atom. Clear, students? So this was about ambiphiles. Now, students, we have covered our types of attacking reagent also. Now we know what is substrate, what is attacking reagent. Now we also know what is reaction intermediate. One thing which is left is types of reactions. We have seen how substrate, how attacking reagent are going to react. What are these attacking reagent? Now what are the kinds of reaction that can occur when these reacts? Now the types of reaction, if I talk about the types of reaction. So basically there are 4 kinds of reaction that we are going to study. The number first is addition reaction. The number first is addition reaction. The number second is substitution reaction. substitution reaction. The third one, students, is elimination reaction. Elimination reaction. And the last one, students, is going to be the rearrangement reaction. The rearrangement reaction. Okay. Now let us start with our very first reaction, that is addition reaction. That is addition reaction. If I talk about the very first addition, the name itself says that something is going to add. Something is going to add over here. Now what happens if I take a reactant molecule as A? Reactant molecule, basically I'm going to use the word substrate molecule as A. And this substrate molecule, yes, I know that with substrate molecule there is an attacking reagent. Yes, so we will consider B as our reagent, attacking reagent. So when this reagent comes and it makes a bond with A, it gets attached to it. That is known as addition reaction, when it gets added to it, and so we obtain a product that is AB. We obtain a product that is AB. So it is the simplest kind which I am explaining you in the terms of AB. When A is reacting with B, it forms AB. It is as simple as it is. Something is being added, you know. Now these are further classified into three categories. The number first that we are going to cover under addition reaction is electrophilic addition reaction. Which one? Electrophilic addition reaction. Now the species that is going to come, the name depends on that only. Now electrophile is going to come and is going to add on, so that's why we have given the name electrophilic addition reaction. Now what happens over here, let us take one case, CH2 double bond CH2. What happens over here? HBr comes over here. We know that electrophile is the one which is electron loving and hence it is positively charged. So if we see HBr, we see H positive and Br negative. So here electrophile is our H positive. So H positive will come over here and attack, and what it will form? It will form CH3 single bond CH2Br. Clear? So first our what will come? First our H positive will come, which is acting as our electrophile, students, which is, you know, electron loving species, so hence it is a positive charge. Now students, now if I talk about in this only electrophilic addition reaction only, alkenes and alkynes are acting as our nucleophile. Why it is acting as our nucleophile? That means this molecule is acting as our nucleophile. As I told you, if this is an electrophile which is coming over here to attack, then this is the nucleophile, right? So these are acting as our nucleophile, students. Now comes the second category, that is referred as nucleophilic addition reaction. Nucleophilic addition reaction. Okay students, if I talk about nucleophilic addition reaction, that means now which species is coming to attack? Nucleophile is coming to attack. Which species will come to attack? To the substrate, nucleophile, and it occurs mostly in the case of carbonyl compounds. Now here is C double bond O, which is carbonyl compounds, and let us say HCN is coming over here. We know that H positive and Cn negative. Now what happens over here? Cn negative will go and attack to the carbon atom. This will go and attack over here, and this bond will break over here. Now which species is going to attack? Cn. It carries a negatively charged, which is the nucleophile. Here now the reagent which is going to react is nucleophile, and hence it acts as an electrophile. So Cn negative will go and attack over there, and what we are going to make here? Here we observe this kind of bond, right? So with O negative, H positive is going to attach and OH will be made, right? So this is the reaction for nucleophilic addition reaction. Now comes free radical addition reaction. The C part is free radical addition reaction. Now students, what do you mean by free radical addition reaction? Now, which will come to attack over here? Free radical. Okay, now let us take this case CH2 double bond CH2, and here HBr is going to attack. Now what is going to happen? Here radicals will be made. What we will observe, all the bonds will break. Here this bond will break, this bond will break, right? And the radicals are going to generate. Like this bond is breaking and creating a radical over here. This is creating a radical over here. This bond is making a radical over here and a radical over here. A radical refers to one electron, right? So here it occurs in the presence of peroxide. Do remember, it occurs in the presence of what? It occurs in the presence of peroxide. So what we are getting over here? We are getting over here CH3 CH2 Br. Clear? So this is the case of free radical addition reaction. Now students, we have covered our first kind of reaction. Now comes the second kind of reaction, that is substitution reaction. The second kind comes out to be substitution reaction. What do you mean by substitution reaction, students? If I talk about substitution reaction, it means to substitute, to take a place of someone else. How I would define it? All I would say is, for example, I am having a leaving group. Kindly consider this. If I am having an X molecule and it is attached with a leaving group, it is attached with the leaving group over here, and it occurs in the presence of, again, what? In the presence of some Y, I would say. So what happens over here? This Y will take the place of leaving group and it will form a bond with X, and the leaving group will leave away. Like this. So what happened over here? One is taking the place of another. One is obtaining the place of another. Now these are also classified further into three basic subcategories. The very first, if I talk about, is electrophilic substitution. Electrophilic substitution reaction, students. Okay, here similarly as we have did in addition reaction, we are going to do in this electrophilic substitution reaction is going to be, for example, if I take here, okay, I have this as my case, and here the electrophile is Cl positive. Now what happens? Electrophilic substitution reaction, electrophile will come and substitute and take the place of this H. So what will happen over here? This H will get removed and Cl will be attached over here. Like this way, Y is taking the place of the leaving group. Here the leaving group is what? It is H positive. It is what? It is H positive, which left over, right? Now this is electrophilic substitution reaction. The second kind, students, that we observe over here is nucleophilic substitution reaction. Okay, if I talk about nucleophilic substitution reaction, what we are going to see, that there is a reactant Rx and nucleophile will come and it will take the place of X. It will take the place of X, and R nucleophile bond will be made and X negative will be liberated out. So this is a kind of nucleophilic substitution reaction. Now the third category is free radical substitution reaction. The next category is free radical substitution reaction. Now students, free radical substitution reaction occurs in the presence of sunlight. So if we take an example of CH4, it occurs in the presence of sunlight, that is in the presence of H nu, that is the energy source, right? So we are taking Cl2 over here, the free radical that is occurring. Now here Cl2 will split like this into free radicals, and they are going to further react. So what we are going to see, the general reaction, I am just writing the general reaction for you to understand what is going to happen over here. See what is going to happen over here. Now, sorry, I have directly written CH3Cl over here. Here hydrogen will come. Now, this will be separated as HCl and CH3Cl will be obtained. Now see, this is basically one step, two step, three step reaction which it occurs in the presence of sunlight. One by one the radical will come and it will attack and the product you are going to get. Okay, so this is free radical substitution reaction. After the students comes the third category, that is elimination reaction. Elimination reaction, as the name suggests, we need to eliminate something, we need to take out something. Now how does it occur, students? Elimination reaction is basically the reaction which two atoms or group of molecules are removed, are eliminated. The reaction in which two atoms or molecules are removed, students. So that is basically elimination reaction, or are eliminated. Now let us take one example. If I take this example over here, so what happens? It occurs in the presence of alcoholic KOH. Now students, as I told you, two atoms or a group of atoms are being removed over here. So here HBr is being removed. Here HBr is being removed, and we observe there is a double bond then arises between these carbon atoms. We obtain an alkene and HBr is separated out. So this is a kind of elimination reaction. Now comes the last reaction that we need to study, is rearrangement reaction. Students, you will see these reactions in the upcoming lectures of class 12th also in detail. For 11th class only, you need to understand what are the kinds of types of reaction, that's it. But when you will study the 12th class, haloalkanes, haloarenes, there you will get SN2 reaction, SN1 reaction. So you will understand all of the kinds of reaction in detail in the coming chapters. Okay, so if I talk about rearrangement reaction, when molecule rearranges itself by shifting its own position, own part to some other part within the molecule. Okay, so why does rearrangement occur? It occurs due to the stability, to attain the stability. If I talk about one case, if I say CH3 CH2 positive, for example, I have this case. Okay, now in this case, what occurs over here? Rearrangement occurs over here. How does rearrangement occurs? This carbocation, to make it stable, comes over here. Now, this is the stability that is being attained. Here, rearrangement reaction occurs. One molecule shifts its position to another atom to become more stable. So, students, this was the end of our GOC section, that is General Organic Chemistry. Now, the important topics. Mostly, I have covered everything in your GOC, but I want you all to practice more and more questions on this General Organic Chemistry. The most important part of General Organic Chemistry is the reactive intermediates, that means the carbocations, carbanions, and the carbon free radical. Other than this, what is the most important topic that we studied about? Electron displacement effects. These are very, very important. Electron displacement effects, you need to be in a command of inductive effect. What is inductive effect? Mesomeric effect, hyperconjugation. These three are very, very important. You should know how to make resonating structures. You should know how to make resonance hybrid. Other than this, you need to practice on the application portion of these effects also. So I want you all people to practice a lot of questions and re-revise all the topics that you have covered in this today's lecture from your notes. First of all, listen, write your notes and re-revise that one time, two time, thrice, and then apply on the questions. So students, practice makes a man perfect. I would end with this quote today. So we will see you in the next upcoming session of organic chemistry. Till then, keep smiling, keep learning. Thank you so much.